Hello and welcome to Astronomy Complete Course. Now, at first, astronomy is a large topic. It's a large subject that includes astrophysics, the study of the mechanics of the cosmos, the orbits and the dynamics of the planets, the stars, and different structures of the universe, even the motion of galaxies, the nebulas, etc. Cosmology, which is more of the chemical makeup of the cosmos, the nebulas, the galaxies, the stars, and the planetary science, discovering what planets are made of, their motion around their suns, the different characteristics of the planets, and stellar astronomy, which is the study of deep space, the study of the galaxies. They are interchangeable, some of these terms, but we're gonna cover a lot of them, and mainly, it includes the dynamics of the stars and the chemical makeups of these stars and everything around them. So it is the study of celestial bodies, anything beyond the Earth's atmosphere, but including the study of the Earth itself, its chemical makeup and its motion around the sun as well. So let's get started. First of all, we're gonna get to the definition of astronomy, the solar system where we live and its planets that are surrounding the sun and rotating around it, the asteroids and comets, the sun, study of the sun itself, stellar evolution and stars, the Milky Way and the formation of galaxies, astronomy measurements and equations, exoplanets, and more. First of all, definition of astronomy. Astronomy in a nutshell is the study of everything beyond Earth's atmosphere. This includes the stars, nebulas, galaxies, planets, black holes and their respective composition, chemical structure, and properties, even their dynamic properties. It involves leveraging math and physics and chemistry and other sciences to try to measure different properties of the cosmos, such as measuring the distance from Earth to the star disk radius, actually the star sphere radius, the disk radius, and the area of the sphere of the star, detecting and measuring the size of exoplanets and their rotation period and properties, and many other things. Now here we notice that we have an equation that we will get to later, which is the relationship between the period of revolution of a planet around the star, the mass of the planet, the mass of the star itself, gravitational constant, and A3. A is the semi-major axis in an elliptical orbit, which is the distance from the center of the ellipse to the longer edge of the ellipse itself. We're gonna explain it more deeply later. Let's start with Mercury. Mercury is the smallest planet. It is the closest to the sun, thus it is extremely hot during the day when the surface is exposed to the sunlight, but freezing during the night due to the lack of an atmosphere that can keep the temperature, that can conserve the temperature. So since it has no atmosphere to conserve the temperature, it is searing hot on one side but freezing cold on the other side. As for the chemical structure, being very close to the sun, it's mostly iron, having a huge iron core and silicate rock on the surface. But how did we find out about it? It involved clever methodologies to collect the evidence. First of all, its heavy weight generated a huge gravity pull affecting its surrounding objects and planets, which suggested the existence of heavy metals in the interior of that planet. Now, the way also it's rotating and it's wobbling, which is called libration, helped scientists identify that there is not a uniform, fixed structure within Mercury itself, and it gave a clue that its structure is not uniform. So when it's heavy on one side and lighter on the other side, it won't perform a proper rotation, so it wobbles, it shakes, it staggers as it's rotating around itself and even around the planet. So this implies a heavier core that is not uniform, that has also ununiform structure on the inside, and that is also a different structure than its surface. So on one side is heavier than on the other side, which makes its rotation not a clean, perfect rotation around the sun. It's almost like the stick shaker of a PlayStation, if you've ever noticed that. And if you ever open a joystick for a PlayStation, you notice that the stick shaker is made of a partial disc that rotates around its axis. Since it's heavy on one side only, it will make the joystick shake. This is how it works. So a shaking object that is performing a rotation implies that its composition is not a uniform. It's not dense or heavy on all sides, okay? It's denser on one side than the other. This is what creates the wobbly effect, which is called, again, elevation. All right? Another point I want to address is the fact that given its proximity to the sun, it will have heavier metals, heavier composites. Why? Because heavier things would induce more gravity, pulling it closer to the sun, which is compared to other planets that are at a farther distance, they will have a lower gravity pull due to the m factor within the equation that we've addressed previously. So it will be traveling further from the sun than a planet like Mercury. Mercury is flying closer. Why? Because its gravity is stronger than the gravity of other planets. So it participates in the gravitational force that is exerted by both Mercury and the sun, pulling it closer to the sun itself. So again, the weaker magnetic field suggested the lack of liquid. Now, the mark, here's like the identifier, the fingerprint. It has a weaker magnetic field. This suggested the lack of liquid, which is responsible for generating a powerful magnetic field due to friction between the liquid, like on Earth, you have a friction, a drag between the water particles and the solid surfaces, creating a magnetic field around the Earth. So that magnetic field is generated again due to the drag and the friction between a liquid and a metallic surface. So less fluids means less friction and a weak magnetic pole. Surface flybys via satellites have photographed a rocky surface, but due to its enormous gravity, which we can calculate through an equation we will see afterward, this suggested a heavier core because it is very massive compared to the rocky surface it has. This implies that there is a heavier core on the inside that's non-rocky, but most likely to be iron core. It's a heavier core because the planet altogether is very heavy to only have rocks as its structure. Today's advanced laser scanning and other available telemetry devices are able to give us even more precise results to assist analyzing the composition of Mercury and other planets as well. Venus, similar to Earth in size but intensely hot. Actually, it's very hot since it has a thick toxic atmosphere dominated by CO2 with thick sulfuric acid clouds. Now, this is what produces what we call the green effect. All right, so having a high concentration of CO2, carbon dioxide, and sulfuric acid clouds can keep the energy of the sun, the heat radiation, on the surface of the planet, okay, which gives us an intense heat and a higher temperature than that of Mercury, okay, due to the greenhouse effect. That's why Venus, despite the fact that it's a little bit further from the sun than Mercury, it is even hotter due to its atmosphere, okay. The atmospheric presence will keep the radiated energy, will keep the heat that is being taken by the sun. The Earth. Now, the Earth is the only planet that hosts life as we know it. It has a balanced atmosphere with a diverse internal structure made of different metals, huge amount of water. Now, here the presence of water is the marker and it's the indicator of the existence of an electromagnetic magnetic field around the Earth, which is available as we know. So the huge amount of water that forms the oceans, seas, and inner Earth waters as well. That water, as the planet, as the Earth is rotating around its own axis, that water create a friction against other metals and other harder structures that create the magnetic field around the Earth. Earth is a rocky planet on the crust, and beneath it has an iron-nickel core. On the inside, the atmosphere is made of 78% of nitrogen, 21% of oxygen. Another interesting thing to note, again, is that due to the presence of water, it will have, and it does have, a powerful magnetic field, which blocks poisonous cosmic radiation. So The magnetic field, it guards the atmosphere and it blocks ultraviolet radiation from reaching the surface of the Earth. More than that, it keeps the atmosphere because the magnetic field holds the atmosphere together close to the Earth, okay? So it keeps it from being stripped away by incoming flying objects such as meteors or flying asteroids that can pluck out the structure and the composite of that atmosphere due to their own gravity. So the magnetic field will hold that structural atmosphere together. It will hold the chemical components closer to the Earth, preventing them from flying away or from being plucked out by meteors and comets from nearby objects due to their gravity. Okay. Next to that, the atmosphere acts as a shield that burns meteors and other objects before they impact the Earth. That's why the Earth does not have a porous surface, unlike the Moon and other planets that don't have an atmosphere themselves. Now Mars is called the red planet due to the rusty color it's characterized by, which implies that Mars used to be covered by water at some point. Okay, so the water is the factor that caused the rusty color of Mars. That's why it's reddish. It used to have metals such as iron, and that iron oxidized due to the presence of water at some point, but water is no more on Mars. So its chemical structure is made of an iron core, a silicate blanket, and an atmosphere mainly of carbon dioxide, CO2 from Mars. An interesting thing about Mars is that it has been a target for multiple space exploration missions such as Spirit and Opportunity, Curiosity and Perseverance launched by NASA JPL and others, I believe. The challenge in landing something on Mars has been the fact that it has enough atmosphere to destroy the craft due to the drag forces, due to the heat, but not enough to decelerate it enough during the approach, okay, to avoid a crash landing. So this has been the challenge in landing rovers over Mars, on the Mars surface. For instance, during the Curiosity mission, a very large parachute needed to be invented, needed to be deployed to slow down the rover after gradually killing the speed of the capsule, which was killed using the drag against the heat shield in front of the capsule that heated up to more than 1,000 degrees during the entry, almost the same heat of the surface of the sun, actually more than 1,000 degrees. Now after that, in the last stage, the vehicle needed to detach. Actually, after the peak heat, the parachute was deployed to slow down the capsule even more. Then the heat shield separated and the vehicle holding the rover on the inside of the capsule started measuring the terrain through a radar. That was after the heat shield separation for radar data collection to detect the terrain. Now, after that, the vehicle detached from the back shell, which is the upper shell holding it by the parachute. The vehicle with the rover detached and started or initiated a powered descent through rockets. Of course, it swiveled around the area of the parachute so as not to hit the parachute as it goes down. And as it started going down, when it became near the surface of Mars, okay, the vehicle could not descend all the way to the ground because of the jet stream of the rockets of the descent engines that would blow the dust inside the rover, damaging mechanisms. It could damage instruments. So instead, it performed a maneuver called a sky crane maneuver. So after detaching from the back shell and during power descent, the rover or the vehicle was lowered the rover using ropes all the way to the terrain. Once the touchdown occurred, the vehicle detached itself, it cut the ropes and flew away to a safe distance because it was in the collision course of the rover. So it flew away and the rover landed on the surface of Mars. This entire sequence was called EDL, or entry, descent, and landing. NASA called it, by the way, 7 minutes of terror, because during 7 minutes, all of these events should have taken place for the rover. And of course, the rover had touched down successfully. Now, again, you see Mars is here, the fourth planet after the Sun, before it Earth, before it Venus, and the closest one is Mercury. Jupiter is the largest planet made of gas, and it's characterized by massive storms spotted as red lines, you see here, traveling around its rotation axis. It has dozens of moons to it. As for its chemical structure, it's mostly made of hydrogen and helium, and possibly has a rocky or metallic core on the inside. Now, the fact of having hydrogen and helium, okay, as lighter gases, because it's much further than the sun, so it can harbor a lot of gases, okay. As we get further from the sun, the gases can be frozen and they form a large part of the planet because they don't evaporate, since the planet has gotten further from the heat of the sun. Okay, this is what characterizes the planets that are further from the sun than the Earth or Venus or Mercury. Of course, Earth also is a special case. It has gases, okay, but it has a magnetic field which keeps the atmosphere intact. Saturn, it's easily identified by its rings made of ice and rock debris. Its chemical structure is almost identical to that of Jupiter, with a massive concentration of hydrogen and helium and a solid rocky core. You notice here, as we get further from the sun, the core becomes lighter and lighter. Why? Because usually the substances that are far away from the sun would be of a lower, due to the fact that the gravity won't be pulling against them as hard as it would pull against iron materials, such as those of Mercury and Venus. Okay, an iron core would usually be closer to the sun due to the gravitational force pulling stronger against these materials to get them closer. So although they are rotating, they are escaping the gravity of the sun, their heavier weight, their heavier core will get them closer to the sun due to the gravitational forces pulling against them between the sun and the planet itself, which is governed by the equation F equals G, small m, which is the mass of the clump of materials that are forming the planet, big M, which is the mass of the sun, divided by r squared. So the heavier the core of the planet is, the closer it would be from the sun. So for Uranus, it's an ice giant planet, okay? You notice it is much further from the sun than the others. Its chemical structure is mostly icy. Now, it makes sense given the fact that it won't be affected as much by the solar heat, made of water, ammonia, and methane, with hydrogen and helium gases that are frozen. The core is made of ice and rocks. Even the core here would be made of rocks, but also of ice. That's interesting also, by the way. So Uranus is an ice giant planet, and its pale blue color is due to the presence of methane gas. Now we start to understand how we can identify the chemical structure of a planet due to the color and due to the spectrum of light that we're getting back from that planet. So how were we able to identify the presence of methane gas on Uranus? First of all, from telescopic observations, Uranus has a blue-green color. Interestingly enough, within a lab environment, okay, when you test what color or what spectrum you can get from the methane gas, these are the two most prominent colors, all right? So these features of the blue and green portray very accurately the presence of the methane gas in lab experiments, all right? Why? Due to the fact that they absorb the sun's red light, okay, red light energy, and reflect back blue and green color bands. Another way to look at it was through spectroscopy that analyzes the light spectrum, which is not only the colors, but whatever frequencies you're getting back from the planet, okay, by stellar observation, by satellites. So for Uranus, or by the Kepler, the telescopic sensor that we have on Earth, for Uranus, it showed a clear absorption of red light. So this is very prominent. Again, it has icy formations of water, ammonia, and methane, also with hydrogen and helium, which are almost available everywhere. And the core is made of ice and rocks. So this reflected the same behavior of the methane gas. As we mentioned, the presence of blue and green colors. Neptune is the farthest from the sun, as you see here. It has a deep blue color and it's characterized by supersonic winds due to the fact that, it has a fluctuation. Usually, fast winds are due to the fluctuation of temperature. So when it's hit by the sun, okay, and also its chemical structure is mainly made of gases, okay, so these gases evaporate and they are stirred by the sun as they heat up, and you have on one side they are heated up, on the other side they are cold. This is what creates the current or winds, right? The difference of atmospheric pressures between two sides. And since you have a large disparity of temperature, you have from one side it is cold, extremely cold, from the other side it heats up due to its exposure to the sun. This is what creates supersonic winds in such case. The chemical structure, it is another ice giant, rich in water here, ammonia, methane, hydrogen, and helium. Again, going back to how we figured out the chemical structure and were able to detect the presence of the different gases and water on Neptune, along with other planets described before. The investigation involved telescopic observation in the early stages, observation of the colors, meaning an attempt to identify the chemical structure from the color of the planet. But later, spectroscopy, which is more accurate and more elaborate way of looking at things, is the science of dividing the light spectrum coming back from the planet and detecting the missing wavelengths, the wavelengths that were observed and the ones that were reflected from the spectrum. This indicates the sort of light rays that were absorbed again, and you can identify what types of gases, what types of substances we have on that planet. So, measuring the magnetic field, now here it comes again. So, we identified a magnetic field which is a direct indicator and is in direct correlation with the presence of water. This is how we get a magnetic field. Okay, the water is a good conductor of electricity. So as the water travels around a metallic surface or around a harder surface, not necessarily metal, it generates a magnetic field. Now you might still have residues of metals even in these planets. Okay, so the presence of water generates a magnetic field as the planet evolves and rotates around its own axis. This is what it creates the drag. So that's on one hand. Density and mass. The mass and volume were measured by studying the motion of the planet and its moons, by the way. Now the moons that are traveling around Neptune will be a great indicator of the mass of the planet, okay, using the velocity versus the gravity and mass and the radius. All right, so the gravitational force F equals gm over r square will be pulling the moon harder toward the planet when the planet is heavier, right? And after measuring the volume, we can get the density of the planet, which won't be uniform by the presence of only the gases that we mentioned before. This is how you start figuring out, okay, you have a heavier core, you have the presence of water, which explains why the density is distributed in a certain way, right? Which why you have that density value. Okay, when we have different heterogeneous layers. Why? Because the mass of the planet, okay? And you know the volume, there's no way the mass and the volume could conform with the presence of gases only, for instance. Based on the formula rho equal m over v. The density is equal to the mass divided by the volume. This is how you identify the presence of other substances, other materials. So to identify these layers, missions were sent to detect the surface structure of the planet by measuring colors, temperature, and by comparing their estimated mass with the overall mass of the planet identified through its motion, right? We can estimate by that the presence of heavier and denser core. So measuring by the magnetic field can also be done using like a transponder or a receiver, magnetic transmission receiver, or an antenna. You call it whatever you want. You can have, just like the antenna works for telecommunications, you can have a receiver to detect and identify the presence of the magnetic field, because it will create an inducted current. So this is a direct indicator of the presence of water, which by traveling around a metallic surface or metallic structures generate a magnetic field. Pluto. Now, there has been a debate over whether Pluto can be considered a part of the solar system, given the fact that it is smaller than Earth's moon, considered as a dwarf planet, and it follows an elliptical orbit around the sun, unlike other planets. So they were confused about naming it a planet or not. Okay, so Pluto, now given its elliptical orbit and its vast distance from the sun, it has a very cold temperature due to the vast, how far it is from the sun, and which is around minus 230 degrees Celsius or 380 Fahrenheit. Most of its journey that it travels, it goes far from the sun, except when it is at its perigee. Perigee is the part of the ellipsoid where this planet gets the closest to the sun. Okay, it's the lower part of the ellipse. It has an icy and rocky surface. It has become obvious at this point why, with mountains made of icy water and plains made of frozen nitrogen. Now this is an interesting structure. It has mountains made of water that is icy, and the plains or the valleys around these mountains are made of frozen nitrogen. It has a tiny atmosphere of mostly nitrogen with some traces of methane and monoxide. The biggest of its moons is Charon, which is so big relative to Pluto itself. Now here is something very confusing, that like the moon of the planet is as big as Pluto, as if they were like twin planets rotating around themselves, because the barycenter, in such case, the center of rotation of evolution, would be in the middle, right? It won't be close to the center of gravity of Pluto itself. The core is made of rock and crust. The crust is mostly water. The crust, which is the covering layer of Pluto, is mostly water ice covered with some nitrogen and methane. Now, planetary mass and other measurements. Let's consider a satellite orbiting a planet in a circular trajectory like this one here. Given the circular pattern, the satellite is in a dynamic equilibrium. All right, dynamic equilibrium meaning that given the circular orbit, you would have a constant speed. Constant speed means no acceleration, zero acceleration, orbital acceleration, and even zero angular acceleration, which complies with Newton's second law of equilibrium, stating that in such case the sum of all the forces would be zero. Why? Because the acceleration is zero. As you know, Newton's third law is sigma F equal ma. The sum of all forces, of course a vectorial sum, is equal to the mass of the system times the acceleration. So hence, in such case, the gravitational force, which is capital F, would be equal, that by the way pulls the moon toward the planet, would be equal to the centrifugal force, which is a force that is created, okay, it occurs due to the rotation. When you're evolving around a planet, the moon, as it evolves, there's a force due to the evolution, due to the revolution rather, is created, which is the centrifugal force. By the way, this is the same force that you feel when you're driving a car and going through a roundabout. This is the force that pulls you outwardly, okay, whenever you're turning your car. So the gravitational force again is equal to the centrifugal force, capital F is equal to small f. which is, by the way, centrifugal force is pulling the satellite or the moon outwardly from the center of rotation, which is the center of the planet, given like the relative small mass of the moon compared to the mass of the planet. Right? This is like the special case of having a moon much smaller than the planet itself, where around which it is rotating. So the gravitational force in such case, big F equal G M. This is the formula of the gravitational force. F equal G small m capital M over r square. R is the radius of rotation. This is from the center of the planet to the center of the moon. That's the distance, the orbit radius. G is the constant, universal constant of gravitation. Small m is the mass of the satellite. Capital M is the mass of the planet. As for the centrifugal force, small f is equal to small m. Why? Because this force is only acting on the moon itself or the satellite itself that is rotating. That's the object in motion, right? So small f equal mv square over r. Given that capital F equals small f, gravitational force equal to the centrifugal force, we place them one next to the other. One equal to the other. So given the trajectory is circular again and the satellite is at the state of dynamic equilibrium, F equal capital F equal small f, centrifugal or gravitational force is equal to the centrifugal force. Now by deducting m here and r, you get gm over r equal v square. Hence v, or the velocity, orbital velocity of the moon around the planet, is equal to square root capital G, which is the gravitational constant, times capital M, which is the mass of the planet, divided by r, which is the orbit radius. This is how we get the velocity. And if we have the velocity, we can figure out the mass of the planet. How can we figure out the orbital velocity? You try to, if we get the period of rotation around the planet, and you have the perimeter, which is you can get from the radius of the planet to PR. Okay, so you have the period, you have the circumference length, you can get the velocity, because distance traveled is equal to velocity multiplied by time, the period it takes for the moon to go around the planet. So planetary mass and other measurements. Now we have G, which is the gravitational constant, as we mentioned, the radius of movement, which is the distance from the center of the planet to the center of the satellite, can be measured, especially when you send a probe as a satellite. It can use reflected laser beams to measure the distance between itself and the surface, right? And then you add up the radius of the planet and the radius of the moon. If you have a artificial satellite, it won't have a radius. Okay, so d prime. Now, by the way, this is how you get the distance from the satellite to the planet's surface. If you have an artificial satellite around a planet, d prime, the distance is equal to, you send laser, right? The distance is equal to laser speed times the time it takes for the signal to go from the satellite all the way to the surface of the planet. Now, given the fact that it will go a round trip, forth and back, so it will go from the satellite to the planet and then it will be reflected and returned, so it is traveling the distance twice. That's why you need to have d prime should be, okay, it is 2d prime, okay, 2 times d prime equal the velocity times the period, right? Okay, so here you have, and at first the distance, this d prime is right, the radius of rotation minus the radius of the moon and the radius of the planet, all right? Because d prime is the measured, it's not the entire radius of rotation. We have g, which is the gravitational constant on the side. Now the radius of movement, which is the distance from the center of the planet to the center of the satellite rotating around it. can be measured, especially when you have advanced technology. You can send a probe as a satellite round the planet, all right? It can use reflected laser beams to measure the distance between itself and the surface, and then you add up the radius of the planet, all right? So the distance, as we know, is equal to the speed of an object moving multiplied by the time it takes it to travel that distance. So d prime equal laser speed multiplied by time. However, here the signal will go forth and back. It will travel twice the distance. Why? Because it is first sent from the transponder, it hits the surface of the planet, and then it is reflected back, measured. Like time cannot be measured on the planet itself. It hits the planet and then it is reflected and collected back by the receiver. This is when you measure the difference between the two timestamps. Let's say it was sent at t equal 1 second and received back at t equal 5 seconds. So the time difference is delta t equal 5 minus 1, which is 4 seconds. That would be the time, all right? As for the distance, we need to divide the distance by 2. Why? Because the signal is traveling twice the distance, correct? So 2d prime equal VL, velocity of the laser, which is almost equal to the speed of light in empty space, multiplied by time that it took to travel that distance back and forth. So d prime, or the distance from the satellite to the planet, is equal VL, speed of laser, multiplied by t, the time it took for the signal to make that round trip, divided by 2. All right? And by the way, d prime is the radius of rotation, or orbital radius, so to speak, minus the radius of the moon or the satellite. If you have a flat satellite, you don't have such radius, minus r planet, the radius of the planet, which you can figure out by using measurements and calculations through observation, by the way. All right. So again, the gravitational constant is G equals 6.67430 times 10 to the power minus 11. But how can we measure the planetary mass here? We need to get the rotation or tangential velocity, or in other words, the orbital velocity. So how do we get that? Based on the formulas presented when you have a circular trajectory or circular orbit, F, gravitational F, is equal to centrifugal F. So basically, F equal capital F equal small f, you get the velocity is equal to square root gm divided by r. All right. So if we know the velocity, we can get the mass of the planet. Mass of the planet is equal to v squared times r divided by g, which is the gravitational constant. The velocity by which the satellite is traveling around the planet is the distance traveled divided by the period of one full cycle, one full rotation, right? So we can measure the time, and by the time get what? Get the velocity, okay, the speed of the satellite around the planet. How do we do that? Again, the distance traveled is equal to the orbital velocity multiplied by the time. All right? So d equal vt, d equal distance divided by time. The distance is what? The circumference of the orbit, which is 2 pi r. R, of course, the radius of the orbit, which is from the center of the satellite all the way to the center, gravitational center of the planet, divided by t, which is the period. You can track the period, the time it takes for the satellite to pass again over the same reference point. This is how we can get the period. From the period you get the velocity, and from the velocity, since we have now the velocity, the radius already, and g, of course g is a constant, you can get the mass of the planet. And by the way, again, from the radius you can get the volume of the planet. This is how they figured out the density of the planet, and of course estimated the chemical or substance structure and internal architectural structure of that planet, what we mentioned before. On one side, we now have the speed of rotation or orbital velocity, and on the other, the formula by which we get the mass of the planet. Starting from the first one, distance equal velocity multiplied by time. So the velocity around the planet of the satellite is equal to distance divided by time, or period, if you will, equal 2 pi r, because it's a circumference, divided by t, which is the time it takes for the satellite to orbit the planet. The mass of the planet is equal to v squared times r divided by g based on the former equation from the previous slide. We combine the two together. Basically what you do is you take v here, the value of v, which is 2 pi r divided by t. You replace it by v, which is in the second equation, and it is squared. Okay, so you take the square of that value. You measure the square of that value. All right, and what you get is the mass of the planet is equal 4 pi square r to the power of 3 divided by gt square. Now r is in meters, the mass is in kilograms, and the period is in seconds. And of course g, gravitational constant, is 6.67430 times 10 to the power minus 11 meter cubed, kilogram minus 1, etc. Okay, these are the international system standards. D is the orbit's perimeter here, which is 2 pi r. T is the rotation period. V is the tangential or orbital velocity. All right, and by the way, if you switch T to the other side and replace, and like if you swap T square and the mass of the planet, you get Kepler's third law of motion, which is T square equal 4 pi square divided by gm for circular orbits, of course, times r3, the radius to the power of 3. All right, so to get the overall density of the planet, this is what we just mentioned. Rho, or the density, is equal to the mass of the planet divided by the volume of the planet. What is the volume of the planet? It is 4/3 PR3. Okay, so rho of the planet is equal 4 pi r3 divided by gt square here, by the way. Okay, this is the mass, and v is the volume. So here we need to correct it by writing, let us write it here by a pen. This is t square. This was a mistake. Okay, I'm sorry. Now we combine those two formulas to get the planetary mass based on rotation, radius, rotation period, the gravitational constant. Keep in mind that the planets usually don't have any homogeneous structure, okay, but rather a hybrid one. This is where we mentioned the inconsistency between the density and the assumption that it's all made of rocks or gases. All right, so you would have a hybrid structure. Usually the core is heavier, made of rocks and iron, or rocks and iced gas, depending on the distance between the planet and the sun or the star it is orbiting. All right, and the mantle, which is the layer outside of the core, and the crust would be much lighter. Kepler's second and third law. Johannes Kepler, a German mathematician and astronomer, stated that a planet orbiting the sun would cover the same angular area during the same amount of time, even in case of elliptical orbits. This is Kepler's second law. This is due to the fact that although it would be traveling closer to the sun or the star system, it would be going faster. So on the other hand, when it's further from the sun, it would be going slower. However, the areas covered in both cases are equivalent. So the area covered when it's closer to the sun, it is equal to the area covered during the same amount of time when it's farther, when the planet is farther from the sun. So the areas of these, or the surface of these two areas enclosed by the arc on both sides, and these like this triangle here along with the arc, the areas are equivalent, they are the same. The third law states that a planet's orbital period is proportional to the size of the orbit when talking about elliptical, and of course the same thing is for circular orbit. So let's say you have an orbit that is much larger for Pluto, all right? Since the distance from the sun is a very vast distance, it will take a longer time to travel an entire cycle, to go through a full journey around the sun. However, on the other hand, for closer orbits like Mercury's, it would take much lesser time to travel around the sun because the size of the orbit is smaller. So the period of an orbit is directly proportional of the size of the orbit, or the distance between the sun and the planet. And they are proportional, all right? So p square, this is the relationship. P square, p being the period, is equal to a constant multiplied by the semi-major axis to the power of 3. Semi-major axis and ellipse is actually, if you divide the ellipse equivalently to 4 chunks, that would be the distance from the center of the ellipse to the longer edge. That is the semi-major axis. In the solar system, k equal 1. The constant equal 1 since the distance to the sun is measured in astronomical unit as a point of reference, all right, as a reference value, and the period is in years, so p square is equal to a3. The period of the years around the sun square is equal to the semi-major axis to the power of 3. Kepler's third law. Again, let's derive Kepler's third law from Newton's equations of motion. We've already seen that, but let's review it. Here, instead of the radius, since we have an ellipse, we use the semi-major axis A, which is the distance from the center of the ellipse to the longer edge, as the rotation radius. The gravitational force acting on the planet orbiting the star is F equal gm, small m, big M over A square. So we replace the radius by A square. We've noticed that radius squared by A square, we've noticed that instead of the radius, we would take the semi-major axis, which is from the center of the ellipsoid to the longer edge, as the reference distance of rotation, the reference radius, all right? We would take that into account. This force is counteracted by the rotation around the star, creating a centrifugal force, F, lowercase, F equal mv square over A. So F equal gm, small m, capital M over r square, that's the gravitational force, g being the gravitational constant again. Lowercase f is the centrifugal force, equal mv square over r. As we know, the distance traveled is equal to the velocity multiplied by the time it takes to travel that distance. So distance equal velocity multiplied by time. Distance here is the perimeter of the orbit, considering it to be circular. At first, d equal 2 pi r. Time is p, actually, the period of one for rotation around the star. So velocity is equal to distance divided by time. All right, you square it, so v square is equal to d square over p square. The distance is again the perimeter of the orbit, which is 2 pi r. Square divided by p square is r square divided by p square. The centrifugal force in such case is equal to mv square over r. We replace v square by 4 pi square r square over p square, and you get this relationship between the centrifugal force, the period, and the radius, right? The radius of rotation. Actually, we can cancel r here, and we would remain with 1r instead of r square, right? Again, so you have f equal m 4 pi square r square pi square times r, and you get that next to f, because centrifugal force is equal to, the gravitational force here is equal to the centrifugal force. So gm, small m, big M, p square times r is equal to m 4 pi square r to the power of 4, and from which you get the period, p square is equal to 4 pi square r to the power of 3 divided by gm, with m is the mass of the planet itself. by replacing r with a semi-major distance, axis distance, which is a in an ellipse, we get the period in an elliptical orbit. This is Kepler's third law. So the closest point here is the semi-major axis we were referring to. Okay, this is the semi-minor axis. Now r has a relationship with a, which is r equal a times 1 minus e, which is the eccentricity. Farthest point apopsis, which is farthest point of r, which is here, okay, would be equal to a times 1 plus e. E again is the eccentricity or the stretch from the focal point. The focal point of the ellipse, let's say it's here, that's the stretch. So F equals G, lowercase m, capital M over R T square, okay, because R is a function dependent of time. Thus, T square is equal 4 pi square times a to the power of 3 divided by G, capital M plus lowercase m, in case m is not, like here in this case, lowercase m is the mass of the moon, which is considered not to be negligible. It has a relatively larger mass in front of or compared to the mass of the planet, unlike a mass of a small satellite. If the central mass m is not moving, you can remove m from the denominator, all right? So this is where m is removed, when the central planet is fixed. But here, in such case, if we consider m, it means that given that the small m of the moon or the satellite is large enough, okay, the center of gravity would not be the center of the planet itself, and both will be moving around each other. All right, so going back to the detection of gas through spectroscopy, which implies or which leads to identifying the gas or chemical structure of a planet based on the bands, the frequency bands we are receiving from that planet. There are three types of interactions that can happen between gases and light. First of all, absorption. Each gas has its own molecular structure and atomic composition that matches different energy levels and can selectively block some wavelengths without the others based on the energy levels of these atoms. All right? Emission. Gases also emit light at specific wavelengths due to the excitation phenomena, during which electrons absorbing energy will gain more speed, transitioning to higher atomic orbits, also called energy levels, and once they fall back to their meta-ground state, original orbit, they release a photon, a wavelength equivalent to the one that was absorbed. This photonic release will appear as an emitted light of a specific color for each wavelength. And finally, scattering. Gases scatter certain wavelengths like water scatters light, right? Usually higher frequencies get scattered more due to their inability to penetrate the gas. The concept is that for a wavelength to traverse an obstacle, its magnitude or its lambda wavelength needs to be greater than the thickness of the obstacle for it to travel through it without being reflected. All right? Going back a little bit, okay, for absorption, is this clear? Each gas has its own molecular structure, atomic composition that matches the different energy levels, and can selectively block some wavelengths without the others based on the energy levels of these atoms. Gas detection through spectroscopy. Based on lab experiments, these are some gases and their interactions with light. Oxygen, O2, it displays a strong UV absorption for the wavelengths absorbed. Colors and effect produced, it produces the visible blue color due to Rayleigh scattering like Earth's atmosphere. Nitrogen, N2, minimal absorption in the visible spectrum and scatters blue light, so it contributes to blue sky through scattering. Carbon dioxide, CO2, it displays an infrared IR absorption around 4.26 micrometers. For the colors and effects produced, transparent to visible light contributes to greenhouse effect, meaning the conservation of heat and temperature. H2O gas, which is water vapors, wavelengths absorbs in the infrared range, no visible effect, but it traps the heat detectable through temperature measurements. Methane, CH4, which we saw in the case of Neptune or Saturn, both actually, absorbs infrared near 3.3 micrometer up, no direct visible light effect, but it actually produces two colors. It emits two colors, the blue and the green colors. Sodium vapor, Na, absorbs and emits at 589 nanometer, which is the yellow frequency. Produces strong yellow glow. This is how we identify the existence of sodium. Neon, Ne, emits red-orange light when excited by light. Okay? So it emits a red to orange light. Cause and effects: classic bright neon light through emission. Hydrogen, H2, absorbs and emits in ultraviolet and visible Balmer series. Pinkish cause and effects: pinkish purple glow in hydrogen discharge tube. Here we note that the visible spectrum is above the infrared and below the ultraviolet. So beyond that range, you would need some kind of instrument to detect these wavelengths, not the visible eye, okay, not the through observation. So from lowest to highest frequencies, respectively, from low frequency infrared or longer wavelengths to high frequencies or ultraviolet shorter wavelengths. This is, we can see within, and the infrared and ultraviolet not included, by the way, but within that spectrum range, light is visible. Beyond that, meaning from infrared down to ultraviolet up, we can no longer see these frequencies by naked eye. Asteroids. What are the asteroids? Asteroids are rocky bodies that form from a debris orbiting the sun. They are much smaller than planets, so they don't qualify to be planets, okay? They don't have also a proper form to them, a circular form that is created due to the equilibrium, the mechanical equilibrium. When the matter structure starts rotating, okay, it naturally forms into a spherical shape. Asteroids don't have that. They have unique, non-uniform shapes and composition. There's a theory proposed by archaeologist and researcher Timothy Alberino stating that asteroids are actually broken pieces of regular planets. Alright? They are located between Mars and Jupiter into what is known as the asteroid belt, and they travel near Earth and beyond Neptune. Alright? So, they are located between Mars and Jupiter into what is known as the asteroid belt. They travel near Earth, beyond Neptune. Others are near Earth asteroids, or NEAs, which have the potential to impact the Earth, actually. Some are called Trojans because they follow the same orbits as other planets. So they trail other planets, alright? It's like they are attracted by these planets and they follow through the same orbital trajectory. Usually they are composed of rocks and harder materials such as heavy metals, usually iron and nickel at most, with some of them having some ice formations on the surface. Their sizes range from very tiny, you would call meteors, to 1,000 or thousands of kilometers wide, like Ceres. Given their small size, they have a weaker gravity for the small ones, okay? Even the larger ones, compared to planets, they have much weaker gravity than the planets themselves. There are three main types of asteroids. You have the C-type, which is mainly formed of carbon. It's like a charred carbon, okay, a burned carbon, very dark in structure. It has a gray-black color, which makes up 75% of the asteroids. The S-type, which is formed of silicate rocks, silicaceous, and mainly silicate rocks, and metals, the appearance is brighter, which is 15% of the asteroids. Given that they have metals, they will be more shiny than the carbon-like C-type asteroids. And the M-type. M-type asteroids are mainly metallic, formed of mostly nickel and iron, and they have a very glossy appearance. They shine much brighter due to the reflectivity of the metallic structure from which they are composed. And these ones are rare in the solar system. Metallicity. So, in an attempt to identify the metallicity and chemical structure of an asteroid, scientists use a method called spectroscopy to determine its composition. So, what do we mean by spectroscopy? First of all, collecting reflected light via telescope, which is a large spectrum of frequencies ranging from near infrared to visible light. Measuring the spectrum and identifying the wavelengths and their respective magnitudes, the amplitudes of the wavelengths within the signal. Hence, any bands that were absorbed will be identified through a plunge in their intensity. It means that since their amplitude has dipped down, this leads to the conclusion that these wavelengths have been absorbed by the surface of the asteroids. Based on lab experiments, different metals absorb and reflect different wavelengths, which can give us a fingerprint of the type of metal or structure that we're dealing with in that case for that asteroid. Asteroids, metallicity, detection, and measurement. What characterizes metallic structures is their high reflectivity and, in consequence, a shallow light absorption. So you would have a return of signals that is flat and featureless within the spectrum of visible and near infrared wavelengths. What flat and featureless means? Let's break them down. Flat means that all the wavelengths that were returned did not have any dip in some specific wavelengths, a dip of amplitude or magnitude. They are returned at the same level without any significant particular absorption of specific wavelengths. And featureless means all the wavelengths that were sent were reflected back. They were received by the receiver. And uniformly, without any one losing its amplitude relatively to other wavelengths. They also have a strong reflectivity towards a radar signal. This is what characterizes metallic structures the most, meaning that for radar signals, which are of longer wavelengths, they are mostly reflected back without any absorption by metallic structures. This is why we have satellite dishes and other antennas are made of metal, right? So for different wavelengths, between 0.4 and 1.0 micrometer, the feature is flat, no dips in specific wavelengths, with slightly a red slope, a slight red dip in the infrared or in the red wavelengths range. Interpretation: this indicates a metal or silicate. Now, around 0.9 nanometer, micrometer, you would have a weak band, meaning that the band that was returned, it has a weaker amplitude than the one that was expected, right? So the interpretation for that, of course, would be a structure formed of oxidized metal or pyroxene, which have absorbed a part of the different wavelength, meaning they have absorbed the band that was sent. Okay, that's why you have a weaker band. So you have a dip in the power or magnitude or light intensity being received due to an absorption. This makes sense since you have here an oxidized metal instead of a clear metal. The oxidization will absorb a part of light, or you would have a pyroxene structure. For wavelengths greater than 2 micrometers, the feature is no strong water features. Okay, interpretation, you would have dry and possibly metallic. So it's a featureless reception, all right? No significant dips in the different wavelengths. For radar signal being returned from an asteroid, this means that the feature is strong. Particularly, what it means is that all the radar signals that was sent has been almost completely returned without any significant absorption. The interpretation for that is a high metallic structure. That's why, again, we use metal for satellite dishes to reflect back the signal coming from the satellite to the receiving device mounted point on the foci of the parabola of the satellite dish. As we notice in the upper table, longer wavelengths such as radar radio waves or radio signals are the most reflected by metal surfaces, unlike shorter wavelengths which are more likely to be absorbed by these surfaces. So this is actually due to metals having an abundance of free-moving electrons that respond to the oscillating electrical field of incoming electromagnetic waves, which would lead to a resonance. At longer wavelengths, such as the radar's signals, the metal's electrons have enough time to oscillate in phase with the electromagnetic waves. This in-phase movement leads to strong reflection rather than absorption, so the metal surface acts like a mirror, just like a satellite dish to a radio transmission from a satellite. Meanwhile, for shorter wavelengths, having higher frequencies, much higher, the electrical field bounces too fast for electrons to resonate in phase with the free-moving electrons of the metal. So this will get them to be absorbed because they have a much higher energy, much higher momentum than the electrons that are available on the surface of the metal. That's why they would be either absorbed or scattered by the surface, but not reflected. Now let's take a look at different spectral fingerprints for different metals, noting that it's not always an accurate approach, given that asteroids can have irregular residues on their surface. However, we can narrow down the possible answers to what we're looking for. So for iron, or Fe, the key spectral features is a flat or slightly red-sloped continuum, shallow band between 0.9 to 1.2 micrometers. Flat meaning that there are no dips in different or specific wavelengths. You have a return of a uniform, same amplitude, same power for different wavelengths that are being reflected. Reflectance characteristics, the reflectance is, so we have a flat spectrum in visible near infrared range. In the visible near infrared range. This is what VNIR means. Notes, pure iron is highly reflective at radar wavelengths, as we mentioned before. Second is nickel or Ni. Similar to iron, little to no distinct absorption in different bands. As for similar reflectance to the iron, almost the same thing. As for nodes, often alloyed with iron. So nickel is always or is often alloyed with iron, which is typical of M-type asteroids, meaning that you would have an iron soldered or like melt with nickel together, forming a composite material for, especially in the case of M-type asteroids, which are mainly metallic. Iron oxide, FeOA. Here, in such case, the key spectral features, you have an interaction with the broad band 0.9 micrometer or 0.6 micrometer. It is absorptive and it will give a reddish spectrum. For the reflection, it will be reflective for red spectrum. This is seen in weathered or oxidized iron surfaces. So when you have an iron surface that is weathered, rusty or oxidized, okay, it will give a reflection of a reddish spectrum. The same thing that we notice over Mars. This is one of the key features of the surface of Mars. Oxidization of iron through water. As for the magnesium, it lacks strong bands in the visible near infrared range. Alright? Lacking strong bands in that area, it will have a low to moderate reflectance, usually detected as part of silicates like olivine, pyroxene, rather than pure magnesium. Alright? Now, also another key word I need to explain here, the albedo. Albedo means how much light is being reflected from a surface versus how much is received. Okay, in case we have that word occur in the next slides. But again, I want to point to something. So for the iron, as a reminder, you have a flat or slightly red sloped continuum, okay, a flat spectrum near the visible near infrared range. So in that range you would have almost a full reflection of light, okay, in that band. But for iron oxide, for example, in that range you have 0.9 to 0.6, all right. In that broad band you have a reddish spectrum, okay, and it's absorptive to other bands that are outside of the red spectrum, the red color spectrum. Aluminium, Al, key spectral features is very highly reflective. It has a very high reflectance in ultraviolet and visible light. But since high reflectiveness in the visible light is not a good indicator, what we look for is the reflectance in ultraviolet, the ultraviolet band, which would be the fingerprint of the aluminium being available on that core of metal, okay, whether asteroid or something else. Usually it's not on detected over asteroids, but we're going through different types of metals here. The reflectance characteristics, it's very reflective but featureless, so there are no specific dips of amplitude or magnitude in specific frequencies. So you have like a flat band being returned, okay, a flatness of different wavelengths being received. However, although it is spectrally flat in VNIR, the detection of the ultraviolet among the different wavelengths returned would indicate that we have an aluminium as a main material. All right, titanium, Ti. So you have weak absorptions around 0.5 to 0.6 micrometer in oxides. You have a low albedo overall, meaning that the light that is being reflected has a much lower amplitude altogether, okay? So the entire spectrum being returned has a very low magnitude, low reception intensity, if you will, low light intensity. Copper, Cu, it has strong reflectance in red, absorption near 0.58 nanometers. Reflectance characteristics, you have a reddish spectrum, but the copper is rare in asteroids, all right? So you have a reddish spectrum, rare in asteroids, and strong, very strong reflectance in red, but you have absorption near 0.58 nanometer. So when we have a higher density or a higher intensity in the red wavelengths, okay, you can, and since you have in the reflectance a high reflectance of specifically the reddish spectrum, that would be a powerful indicator that you have copper. For the chromium, possible weak band around 0.43 micrometer, and it has also a low albedo, meaning that you would have a much lower intensity of light, a much dimmer light being reflected versus the amount of light that's being absorbed by the asteroid, often detected in chromite, used as an indicator mineral. All right, so again, here we go through the terms. VNIR means visible to near infrared. Featureless means that there are no obvious dips or spikes in bands. It has like a flat spectrum. The spectrum is fully reflected. Featured, however, means that some bands in the spectrum have been absorbed almost completely by the metal. So for the featured, you have in the case of the copper, a reddish spectrum, meaning that all other bands have been almost completely absorbed. So you have a strong reflectance in red and absorption near 0.58 nanometer, and the reflectance in red is versus a low reflectance in other wavelengths. Now, personally, I do believe that asteroids are fragments of planets, as Timothy Alberino stated, unlike the mainstream theory stating that these were formed since the inception of the cosmos, basically, by matter gravitating to each other. Now, it can be also the case for some asteroids, but not always. And these same matter that formed some planets formed others asteroids as well. Okay, formed asteroids as well. So the part that detached from the planet will determine the asteroid composition in most, whether C, S or M type, and also what kind of planet got broken off. In other words, if the fragment broke off the crust, which is like the outmost layer of a planet, it will be mainly of water and gases and carbons, forming the C-type, the charred C-type asteroid. Meanwhile, if the fragment of the planet that broke off was the mantle, which is mostly made of rocks, that's the inner area underneath the crust, and between the crust and the core, apart from the core, it will be in part silicate and in part iron or another metal, but mostly rocks and silicate, which will produce the S-type asteroid. Otherwise, if the part that was broken was part of the core formerly, it will be mostly metallic, which gives us the shiny M-type asteroids that are heavier and glossier or more shiny than other parts of the planet. Interestingly enough, there's a description of an asteroid impact in the book of Revelations, chapter 8 in the Bible, where it portrays a massive rock falling from the sky, which is the asteroid, of course, and its name is wormwood, or in another translation, bitterness, or aphesantine, which is in the Greek translation, the Greek word. So, then the second angel blew his trumpet, and a great mountain of fire was thrown into the sea. This is an asteroid going through the atmosphere, burning with the fire, with plasma due to the drag forces against the atmospheric air particles. So 1/3 of the water in the sea became blood, okay, due to the massive loss of the water creatures, the sea creatures basically, and probably due to the fragmentation of the structure or the contents of the asteroid, coloring the water of the seas with pitch black. 1/3 of all things living in the sea died, and 1/3 of all the ships on the sea were destroyed. Then the third angel blew his trumpet, and a great star fell from the sky. So probably this is the first impact, right? Because it has a debris that might impact first, before, like, they might reach the Earth before the larger asteroid body, due to the reduced amount of drag forces. So it might penetrate faster the atmosphere than the main object, the main asteroid. All right, so then the third angel blew his trumpet, and a great star fell from the sky, burning like a torch. It fell on 1/3 of the rivers and on the springs of water. The name of the star was Bitterness. It made 1/3 of the water bitter, and many people died from drinking the bitter water. This is, by the way, a prophecy about the end times, for those interested to know. Okay, this is yet to come. Then the fourth angel blew his trumpet, and 1/3 of the sun was struck, and 1/3 of the moon, and 1/3 of the stars, and they became dark. This is probably, or mostly even, due to the debris flown because of the impact. That all that dust and rocks thrusted by the impact of the asteroid, they are thrown into the atmosphere, making the entire atmosphere pitch black, blocking the sun radiation, the sunlight, from reaching on the Earth. This is what made the sun dark. It's no longer visible. The moon also darkened, 1/3 of the moon, and 1/3 of the stars were blocked also. They became dark due to the dust in the air, and 1/3 of the day was dark, and also 1/3 of the night. That's an interesting passage, an interesting description of what would happen if an asteroid would impact the Earth. Also, there are parallel verses almost talking about the same thing. So in Matthew, the book of Matthew in the New Testament, chapter 19:29, immediately after the tribulation of those days, the sun will be darkened and the moon will not provide its light, and the stars will fall from the sky, and the powers of the heavens will be shaken. That's interesting. Powers of the heaven will be shaken, probably like a distortion that would be even much worse than an asteroid impact. I don't know what that is portraying exactly, but you would say a distortion in the time-space fabric. All right? Shaking of the powers of heaven, meaning the disruption of the gravitational fields around the planets. It might be something, a bigger event than a simple asteroid here. Also, a parallel verse talking about the same thing concerning the darkness over the Earth, mostly due to an asteroid impact thrusting all dust particles into the air, is in the book of Joel, chapter 2, verse 31 in the Old Testament. The sun will be turned into darkness and the moon into blood before the great and terrible day of the Lord comes. The Lord Jesus, of course. Now, moon turning into the blood, probably due to a partial blockage of the atmosphere due from the dust particles. As we know, and by the way, this is very scientific, the moon turning into blood means it's only giving the red reflection. It's only reflecting the red light, which is very interesting and significant at the same time. Why? Because it happens to be that red wavelengths are the longer wavelengths. They have a larger penetration than the blue and the green, which are shorter wavelengths that are most likely to be blocked by, a layer of dust. Meanwhile, the red wavelengths, since they are longer, they can go through that layer and reach the surface of the Earth. Because the theory here of waves propagation is that for a wavelength to go through a barrier, the length of that wavelength, the lambda, should be at least greater than or equal to the thickness of that barrier. All right? So when you have a thicker barrier, only longer wavelengths or shorter frequencies, in other words, such as the red wavelengths, can pass through. Others will be blocked by the layer of dust in such case. Impact physics. Let's talk about the impact physics of asteroids. So the kinetic energy generated from an asteroid impacting the Earth is 1/2 of the product between the mass of the asteroid and the square of its velocity. So this kinetic energy is measured in joules, mass in kilograms, and velocity in meters per second, which is the international system of metrics. Now, if you notice something, that the velocity is more significant than the mass itself. Why? Because it is multiplied by itself. The velocity is squared, meanwhile the mass is divided by 1/2, you can say. That's why the bullet, although it is very light in weight, the impact of a bullet against an object is more significant due to its high velocity. So although it is a lighter object, the damage incurred by the bullet is mainly due to the high speed that it travels, which is close to the speed of sound, if not even beyond the speed of sound, because that speed is squared, meanwhile the mass is not. That's why the speed itself is more significant in the kinetic energy than the weight of the object. So the energy generated by the asteroid that caused a mass extinction called the Chicxulub, Chicxulub, which impacted in the Yucatan Peninsula in Mexico, Southern America, was around 10 to 15 kilometers wide, 6 to 9 miles. Estimated mass 1 or 2 times multiplied by 10 to the power of 15 kilograms, or in other words 1 to 2 quadrillion kilograms, and a velocity of 20 kilometers per second or 45,000 miles per hour. The energy released was so huge, 100 million megatons or TNT. The impact created a crater of around 180 kilometers, 110 miles wide, and 20 to 30 kilometers or 12 to 18 miles deep. This is how huge and colossal the result or the consequences of such an impact. There's no fixed formula that can give us the crater widths and depths generated based on the width, weight, and speed of impact of an asteroid. Alright? Since there are other factors in play here, such as the soil structure, the asteroid's chemical makeup involved. However, looking into previous data collected throughout history from past impacts, we can have an estimation, an estimation or estimated formula over how we can approximate what crater size or width we would have and what the depth of such an impact would be based on the input of asteroid widths, traveling speed, and weight. So let's look at some of the historical impacts. You have the Poppy crater in Siberia. The asteroid width was about 5 to 8 kilometers, estimated like that, and we could estimate that by running similar experiments in Ames Research Center, for example, where you have a ballistics research going on, and they measure the size of the crater created and the depths relative to the weight of the ballistic, which would be a metallic sphere, the speed of impact, and the width of that sphere or diameter. So asteroid width 5 to 8 kilometers in Siberia, traveling speed 15 to 20 kilometers per second, weight around 10 to the power 13 or 10 to the power of 14 kilograms. The crater width that was generated is around 100 kilometers, and the crater depth 20 kilometers. All right. Rutherford crater, also in Siberia, asteroid width estimated to be 10 to 15 kilometers, traveling speed 15 to 20 kilometers per second, weight unknown. Crater width 250 to 300 kilometers, crater depth 20 to 25 kilometer down. Okay. Third event we have here, Tunguska event, also in Siberia, interestingly enough. The asteroid width was estimated to be around 50 to 60 kilometers, traveling speed around 15 to 30 kilometers per second, weight 10 to the power of 7 kilograms. Here in such case, no crater was generated. Perhaps it fractured right before impact, or it fractured right on the surface, on the terrain, when it had hit. However, the crater, instead of the crater width, we had a shock wave and a flattening of 2,150 kilometers squared of forest. Okay, we're going to try to estimate how we can get these measurements in yellow here. So, if you look at it based on previous data, the crater width can be estimated, and honestly, this is my personal observation. Okay, by approximating, the values, you can find that there's a relationship between the crater width and the asteroid width, related also to the impact speed. So you can get the crater width by multiplying the asteroid width in kilometers by the impact speed in kilometer per second, and you get the crater width also expressed in kilometers. As for the crater depth, you get the crater width, okay, and you multiply it by either 10% or 20%. Now, what are we basing that on to achieve the crater depth? Okay, we assume that the weight is in the range of 10 to the power of 7 kilograms. Not more than that. Let's check another measurement, or let's do the math in the next slide. So, for Poppy crater, Siberia, asteroid width was around 5 to 8 kilometers, traveling speed 15 to 20 kilometers per second, weight around 10 to the power 13 or 10 to the power 14 kilograms. So let's get the crater width and crater depth without even looking at the values over here. Crater widths, okay, estimated to be the product of the asteroid widths, which is the longer breadth of the asteroid, with impact speed, both expressed in kilometer. Of course, the speed in kilometers per second. At first, okay, so crater widths equal asteroid widths times impact velocity. As for the crater depths, it is, since we have, like, the weight is 10 to the power 14, right? It should be, yeah, 14 minus, pardon me, 14 divided by 7, okay, which is 2. 2, we multiply it by 10%, you get 20%. That would be the crater depth. Not 10, by the way, 20%. So let's run the numbers on Poppygate crater, Siberia, which is a previously observed example in the other page. The asteroid width is 5 to 8 kilometers, traveling speed 15 to 20 kilometers per second, and weight is around 10 to the power 13 or to the power of 14 kilograms. All right, without observing or seeing the results, let's get the results ourselves. So at first, this is a crater event where a crater was generated due to the impact, having a width and a depth. Okay, the crater width estimated to be the product of asteroid width in kilometers with impact speed in kilometers per second, which is the same as traveling speed, by the way. So crater width equal asteroid width times the impact velocity. That's first. As for the crater depth, it is equal to 10% of the crater width, given if the weight, okay, not the height, given if the weight is less than or equal to n times 10 to the power of 7 kilograms. So it doesn't go beyond the power 7 of 10 of kilograms, all right? But in other cases where the weight of the asteroid is beyond that, is higher than that, which is our case here, what we do is the crater depth would be the power, all right, which is, 14, the current power of the weight, the power of 10, okay, 10 to the power 14, so you get 14, you divide it by 7, which is the standard law, if you will, as I noticed, and you multiply it by 10%. So 14 divided by 7, which is 2, times 20 over 100, so it's 20% the crater width. All right, now for Tunguska event in Siberia, what you have is an asteroid impact without a crater being formed. So here we want to measure up the area that was flattened by the asteroid impact. This is how we get it. Okay, so at first you have the asteroid width, 50 to 60 kilometers in such case by estimation, traveling speed 15 to 30 kilometers per second, weight around 10 to the power of 7 kilograms, all right? And the same methodology apply, by the way. But at first, since we have no crater, we have only an area that was flattened, which is made of forest, by the way. It is a non-crater event, like, which is Tunguska in such case. The shockwave blast area is estimated by multiplying the asteroid width in kilometers with impact speed, plus what we usually get by calculating the depth, we add to the asteroid width times the impact velocity. So we have the blast area, again, is estimated by multiplying asteroid width with the impact speed. This was formerly the crater width, and we add to it 10% of the answer, which is 10% of the previous crater in the crater event, okay? And here it is 10% given that the weight is in the power of 7, okay, 10 to the power of 7 kilograms. So the blast area would be asteroid width in kilometers times the impact velocity in kilometers per second plus 10% of that value over here, given that the weight is less than or equal to 10 to the power of 7. N times 10 to the power of 7. All right? Which is, by the way, around, if you do the numbers, it's around 2,150 kilometers square. Okay? So, which is almost, you know, if you do 50 times 30, okay, it's around 1,500 kilometers. You add to them 10%, which is, yeah, 10%, 50, okay, 150, 160, around that, okay? It's not like sharp numbers, okay, but by estimation, you get these numbers as close as possible. So for Poppygay Siberia, let's see the numbers. Asteroid width 5 to 8 kilometers, traveling speed 15 to 20 kilometers per second, weight 10 to the power of 14, we will take it. So the crater width, okay, we will assume that the asteroid width was 5 kilometers, all right? We multiply that by traveling speed. We take the 20, you know, the upper value, which is 20 kilometers per second. 5 times 20 would give us around 100 kilometers, which is the crater width, almost exactly, you know. As for the crater depth, now since the weight is around 10 to the power 14, okay, so you take 14, you divide it by 7, which is you know, the standard law. Again, so 14 divided by 7, that's 2 or 20%. You then multiply it by 10%, that's 20, and you multiply it by the crater width, so that gives you 0.2 times 100 or 20 kilometers. That's the crater depth. All right, so is it clear? Now, for meteors, meteors are small rocks or particles traveling in space, which are miniatured asteroids, okay? So once a meteor penetrates Earth's atmosphere, it will burn due to its friction with Earth's atomic particles, producing a trailing flash of light, all right? These are, you know, the flying stars or the light stars, you know, different names, okay? So due to its small size, most of it burns within the atmosphere and evaporates without even reaching the ground once it is absorbed by the Earth's gravitational pull. And whatever piece survives, it will land on the Earth's surface. Okay, that would be the remnant, usually mostly made of nickel and iron. Okay, depending on the type of the the meteor we are dealing with. As for other planets or moons, such as the Earth's moon, the impact would have a larger consequence, you know, a more dire consequence, and it will form a hole on the surface due to the absence of a shielding atmosphere like the Earth's atmosphere. Because unlike the Earth, the moon has no atmosphere to block it or to burn up the meteor before reaching the surface of the terrain. That's why it would impact with a high velocity, forming a pore or a hole on the surface. That's why you have porous surfaces all around different planets that are other than the Earth, like the moons and most of the planets. Okay, on Earth usually you'd see the larger craters for the asteroids that could have survived the atmosphere before landing and impacting the surface. Comets. Now, a comet is a celestial object made primarily of icy gases and liquids like water, CO2, ammonia, and methane. Usually it comes from, you know, far away from the solar system, or, you know, even from outside the solar system. And given its structure, you know, it is far away from the sun, because this is what allowed these different gases to solidify, okay, to become icy and forming the structure of the comet. So you have icy liquids, icy water, CO2, ammonia, and methane, all becoming solid, okay, due to their far distance, due to the comet's far distance from the sun. When it travels close to the sun, these icy gases start evaporating immediately in a sublimation process, meaning without passing through the liquid state. Okay, they transform immediately from from icy gases to from ice to the gas state. Okay, and they form glowing trails trailing millions of miles behind the comet's center of gravity. This or these glowing tails, you know, are called a coma, and usually they produce at least, in fact, the comet usually produces at least two tails, of which one points away from the sun due to the solar wind, and the other in a different direction due to radiation pressure. Okay, which is, you know, the different direction of the trajectory of the comet itself. And here in a moment we will explain why. So most comets originate from the Kuiper belt, which is beyond Neptune, a very long distance from the sun, which explains why their structure is mostly ice, okay? Because the low temperature would allow for ice formations of different gases to be brought together and, you know, clumping up to form the comet nucleus, nucleatic structure, okay? And it has no tails except when it's being hit by the sun. Okay, this is why we see the tail trailing behind it. Or the distant or the cloud, that's another region where they come from. They travel in highly elliptical orbits, some taking thousands of years to completely orbit the sun. Okay, among them you have the Halley-Bopp comet. Okay, it is very far from the sun with an elliptical orbit. Okay, that's why it's iced up. It's very glassy, and it's very cold. Okay, due to its vast distance. The nucleus or the main comet mass is usually between few to tens of kilometers across. As for the tail, it can stretch millions of kilometers. You know, the gassy tail that you see with your telescope. Structure of the comet. Nucleus is mainly formed of frozen, you know, that's the solid frozen part that harbor multiple iced gases, water, that's ice also, everything in the form of ice, okay? Everything is frozen and solidified, and also some dust that have been, you know, attracted by the nucleus gravity and, you know, and have frozen or have been, if you will, kept, okay, or locked through underneath the icy cloud, the icy layers, okay, of other methanes and gases, okay. The coma, it's a cloud of gas. Yeah, by the way, trapped was the word I was looking for. So the dust, most of it trapped underneath different layers of ice. For the coma, cloud of gas and dust forming the atmosphere surrounding the nucleus that's created by evaporation because of the sun when the comet is nearing the sun, when it's being exposed by the sun radiation. You have an ion tail, stream of ionized gases pointing away from the sun due to the solar wind. More info on the next slide here, okay? That's the first tail, which is facing the opposite direction of the sun, and dust tail, which is facing the opposite direction of the trajectory of the comet itself, and that's the result of a stream of dust particles trailing behind the comet in the opposite direction of the trajectory of the path, okay, on the same trajectory but on the opposite side, in the opposite direction, okay, but on the same trajectory curve. And we will see how the dynamics of both of the tails work, or why they face in these ways, and what are they the result of. ion tail versus dust tail. Let's talk at first about the ion tail and how it forms. When the comet comes near the sun, the icy components evaporate due to the heat without passing in the liquid state, by the way, in a process called sublimation, which is a direct transfer from the solid state to the gas state without passing through the liquid state. After that, the ultraviolet solar radiation, because as we know, the comet has no atmosphere that can block the UV radiation. And the ultraviolet is a very short frequency, having a very high frequency, and thus a very high energy. It strikes these gas molecules that had evaporated, among which you would have nitrogen dioxide, H2O, or water vapors, and carbon dioxide. So it will strike them, releasing electrons in the atmosphere. These electrons, as they get charged or excited by the UV photons, pick up higher trajectories above the atom nucleus. That's how they started picking up. They started distancing from the nucleus until they can no longer be held by the nucleus gravity of the atom itself, and they detach from the atom. So you would have atoms that have become charged positively because they lost electrons, and electrons roaming along with these positive ions in the atmosphere of the comet. As a result, these gas molecules that were neutral lose their electrical equilibrium, as we mentioned, and become positively charged. This leads to positive ions and liberated electrons flying above the comet. So you would have H2O, water vapors, plus a UV photon being excited by an ultraviolet radiation will produce a positive ion, meaning atoms that are positively charged, plus electrons that are liberated, and these two will roam in the atmosphere or in the zone around the comet. Now, when the solar wind, which is a stream of charged particles, when it comes, it sweeps the floating ions and electrons that were released prior by the interplanetary magnetic field, IMF, which is carried by the solar wind, by the way. And it picks up these particles and it transports them away from the sun by the electromagnetic forces within that wind. So, and being hit by the light, they glow as they travel further from the comet, because they are being picked by the interplanetary magnetic field, which is the magnetic field carried by the solar wind, as we mentioned. So they started traveling further from the comet in the opposite direction of the sun. However, as they are being hit by the solar radiation, they will glow as they leave the nucleus, as they travel away. This creates the ion tail facing away from the sun. On the other hand, we have the dust tail, which has different causes of formation and different direction even. By the way, the ion tail is more linear than the dust tail, and we will understand why. As for the dust tail, just like in the case of the ion tail, the sun sublimates the icy gases of the comet that detach from the surface and float above the comet nucleus. The radiation pressure, which is by definition the force exerted by the sun photons, that although are very tiny, they hold no weight to them. It's a very low weight, but still they carry a certain momentum. So they start pushing against the floating dust particles away. Okay, so they start pushing them away by exerting a tiny push, because photons still have a momentum. Although the mass is very tiny, they still have a mass and yet, a kinetic energy to them, a momentum to them. So the dust grains get lightly and gradually pushed by these photons, and they trail behind the comet's orbit in the opposite direction of the trajectory, not the sun. Of course, now the lighter these dust particles are, the farther they are pushed and the faster they are pushed away in the comet trail. and vice versa, meaning that when the particles are a little bit heavier, they will be slowly dragging away, so they will be placed closer to the nucleus or the gravitational center of the comet. That's why you would get a curved shape dust tail versus a linear ion tail. Okay, so unlike the ion tail, which has the form of a line, the dust tail is more curved due to the disparity of the masses of dust particles. So the heavier the dust particle, the closer it would be to the nucleus, and the gravity exerted against them by the nucleus, since they are heavier than gases. Okay, so the heavier the dust particle will be, the closer it will stay with the nucleus. Okay, meanwhile, the lighter it would be pushed further and faster. Okay, let's talk now about the sun, which is the center of the solar system. So first of all, what is the chemical makeup of the sun? You have helium, He is the element symbol, around 27% of the chemical makeup. Oxygen, 0.97%, carbon, 0.4%, neon, 0.13%, nitrogen, 0.10 or 0.1%, magnesium, which is a metal here, 0.06%, silicon, 0.07%, and others. But as you notice, it is mainly made up of helium, which is, a heavy type of gas, but it's a gas. So what is the sun's composition? First of all, the core is mostly ionized hydrogen and helium. This is where the nuclear fusion that generates the radiation power occurs. This is where, the nuclear engine is working at the core of the sun. So it is mostly ionized hydrogen and helium. You have next to it the radiative zone, which is the ionized hydrogen and helium. The energy is transported to the outside. Okay, so the ionized hydrogen and helium from the inside, their energy is transported to the outside via this layer. Then convective zone, which is ionized gas plus plasma, that energy moving by hot gas, it rises up to the surface. Okay, that's the convective zone. Photosphere, which is the surface of the sun. Okay, having a high temperature, very high temperature of 5,500 degrees Celsius. Okay, and it's mainly made of hydrogen and helium. Chromosphere, which is, above the surface. Okay, a layer above the surface, with dominant hydrogen. Helium is visible during a solar eclipse, actually. And finally, the corona, which is the thin plasma layer. It is highly ionized, highly charged particles are there. This is what it means. So highly ionized heavy elements such as iron, and it is extremely hot. So talk about it again. Okay, so to wrap it up or to simplify it, you have the core, mostly ionized hydrogen and helium. That's the center of the sun. This is where nuclear fusion occurs. Radiative zone, this is where ionized hydrogen and helium, their energy is transported to the outside from this zone. Okay, then convective zone, which is a layer where ionized gas plus plasma, their energy moves by hot gas rising. Okay, there's a hot rising of the gases. Photosphere, that's the surface made of hydrogen and helium, very hot, around 5,500 degrees Celsius. Chromosphere, dominant hydrogen and helium, observable during solar eclipse. That's the external glow during a solar eclipse. And finally, corona, thin plasma layer, highly ionized heavy elements such as iron, and extremely hot. So how does the sun emit light? First of all, fusion reactions inside the sun's core happen in 3 stages. Let's watch the fusion reactions. At first, you have the proton fusion. So the main element that is fusing, okay, it's 2 protons fusing together, okay, forming a deuterium, which is a heavier element. and releasing a positron and a neutrino. So mainly you have under very high temperature. This is why the nuclear fusion occurs under very high temperature in the core due to high pressure and high temperature rising. Because as we know, gases under high pressure usually pick up a very high temperature, okay, heat up enormously. So two protons fuse to form a deuterium plus a positive charge, which is a positron, and a neutrino, a neutral charge. Second stage is a deuterium 2H, okay, or H2, fuses with another proton, giving or birthing a helium He3 heavy particle with gamma emission. This is where the production of light takes place. So you have deuterium with a proton forming a helium-3 particle, atom rather, helium-3, which is a heavy material, plus a gamma radiation, which is where the light of the sun comes from. Then two helium-3 nuclei combine to form a helium-4, which is a heavy particle, but also releasing two helium, two H1 protons, okay? And by the way, the helium-4, when it fuses with another helium-4, it starts producing a heavier, eventually leading to an iron core, perhaps. So this is what is lost of the energy of the sun, okay? So He4 can never become something that will produce energy or gamma later. However, these two protons that were released will participate again in proton-proton fusion, and the cycle continues. By the way, the overall equation is 4H1, 4 protons, will give us helium-4, which is a very heavy element, plus 2 positrons, 2 neutrinos. These are charged positively. The latter, they have neutral charge, plus gamma, which is the light radiation. So basically, in the second reaction, there's an emission of gamma wave, which is the light generated by the sun. In the third equation, a heavy body of helium, He4, is created and it's absorbed by the sun core, making it heavier, as we mentioned. But two protons are also released that participate again in the reaction cycle to create more light. Slowly and gradually, the amount of protons generated will decrease until the sun transforms into a red giant, okay? So slowly and gradually, the amount of protons generated will decrease. The fuel will eventually start running out. The fuel is the protons that are available for the fusion reaction within the core of the sun. Until the sun transforms into a red giant, what's called a red giant, when it's no longer able to produce as much light as it used to, while its core becomes heavier and more compact, okay? It will have a more powerful gravity. It will collapse even further upon itself. It will shrink to the inside, becoming heavier as fewer reactions producing gamma rays occur, and the fusion reactions pushing out, because the fusion is what pushes out the radiation, okay, making the sun, push outwardly instead of having it collapse, okay. This is what keeps the sun in its form. The fusion reaction, the hot gases would push it outwardly, okay, while the gravitational force will push the cooler particles that have arrived to the surface inwardly, okay, because they have cooled down. So the fusion reactions pushing out die down due to the reduction in the reserve of protons responsible for that. Eventually, like any other star, the core becomes so dense with an immense gravity that implodes, creating a supernova in supermassive stars, okay. Much will be explained in detail, of course, but for smaller stars, it would lead to a neutron star, all right? Now, for supergiant stars, it will lead to either a black hole or a, neutron. We will check the difference, okay? No, actually, for smaller stars, it can, be reduced to a small core. We will check that in a moment. So these are the three main reactions, fusion reactions, that occur within the sun's core. First one is the proton fusing into deuterium, which is a heavier material, plus positron charged positively plus neutrino, a neutral particle, very light particle. Then deuterium interacting with one proton that will form an He3 or helium-3, heavier material, plus the gamma radiation from which we get the light. Finally, with He3 will produce helium-4, a heavier, much heavier material, plus two protons that will participate again in the reaction cycle. The process of energy generation in the fusion reaction, and that's a review on nuclear physics, okay? So how it works, how does it work? Energy generation in fusion. According to Einstein's theory, mass can be transformed to energy and vice versa using the following equation. C being the speed of light, delta M is called the mass deficit, or the difference between the mass of the product of the reaction versus the mass of the reactants themselves, the elements participating in the reaction on the left. So it's the difference of mass, of the total mass of reactants, between the reactants and the produced materials or atoms and particles. E equal delta M C squared. So let's take back the first reactions equation. We have H1 plus H1, two protons fusing into H2, which is a deuterium, plus positron plus neutrino. Due to the incredibly small weight of an atom, we use the atomic mass unit scale to measure the weight of each component. The mass of each element needs to be divided by the atomic unit value to get the mass in atomic units. So, one atomic unit is 1.66 times 10 to the power minus 27 kilograms. This is one atomic unit because we cannot measure particles by kilograms. It doesn't make any sense. We're talking about very tiny bits and particles that are at a very low, standard beyond, the metric measurements. All right. So, taking the first equation in consideration, two protons fusing together, they produce a deuterium plus positron plus neutrino. E equal delta MC squared. So let's measure up the difference between the protons, and which are the reactants, and the mass, total mass of the products, correct? So you have, for the mass of the proton, it's 1.0072764, etc. I take like the most accurate value, which is in kilogram, 1.6726 times 10 to the power minus 27. For the neutron, the mass of a neutron is 1.00866491595 U. Now, for other elements, the mass of electrons is always negligible. No, you see here, it's not actually an accurate predicament. It's not the mass of protons and neutrons that you add up to form or to get the mass of the deuterium. No, the deuterium will have a specific mass of its own. We get that by comparing it to a mole of mass. Okay, 1 mole of a deuterium, how much does it weigh? We divide it by Avogadro's number. We will talk about that in a moment. But we don't basically measure the deuterium's mass by summing up the masses of the protons and neutrons, okay, it carries. Here, the mass of H1 is the same as the mass of the proton because H1 is actually the proton. All right, the mass of deuterium here is, to the right. Actually, you can get that from a chart, okay? The mass, each element has a specific mass in mass units, of course. We add the mass of the deuterium to the mass of the positron, which is 0.000544858, plus the mass of the neutrino, but the mass of the neutrino is very negligible. We don't even take it into account, okay? So, we've gotten the mass of the product, and we get the mass of the two protons here. Mass of the reactive components is 2 times the mass of the protons because you have 2 protons simply as that, okay, among the reactants. So which is around 2.014552933.242. Okay, now the mass deficit is the total mass of the protons, the reactants here, minus the mass of the deuterium plus the mass of minus the mass of the product, which is mass of deuterium plus mass of the positron, without taking into consideration the neutrino, because the neutrino is negligible. Okay, that would be delta M. All right, multiplied by c square, you get the energy generated from that reaction. Now we will see that we don't multiply it by the c square in that sense, okay, which is the speed of light in meter per second, but we have another way to look at it in on the particle level, you know, on particle physics level. But at first we've gotten the mass deficit, what is called the mass deficit. Let's check what we have here. All right, so let's calculate the energy released through this reaction. E equal delta M C square. Now, each one mass unit is converted into 931.494 mega electrovolt at the speed of light. Okay, so each mass unit, each one U, okay, is equivalent to 931.494 mega electrovolt by c square, meaning that at the speed of light, each mass unit becomes 931.494 mega electrovolt. This is the rate of the transformation of a mass into an energy at the speed of light. So the amount of energy released in this reaction is the following: E equal the mass deficit, which is the difference of masses, multiplied by 931.494 mega electrovolt, which is 1.80433 mega electron volt. This is actually the unit of measurement for the energy in particle physics. Now let's calculate the energy released from the second reaction, fusion reaction, in which one deuterium fuses with one proton, or H1, to produce He3, helium-3, plus a gamma radiation which produces light. This is the reaction that actually produces light through gamma emission. Let's evaluate the energy in such case. Okay, so we have at first the mass of the proton is given here, mass of neutron, and let's evaluate the mass of the reactants, which are the deuterium plus one proton. So the mass of the reactants is the sum of different masses here, mass of deuterium plus mass of the proton, which is H1, is around 3.023 to 178 units, okay, because we have M2H, the mass of the deuterium, and we have the mass of the proton given here. Okay, now the mass of the deuterium, I'm not sure if it's an accurate value, okay, I didn't fact check it, but you can look it up to see whether it is an accurate mass of the deuterium. As for the product, now gamma energy has no mass, so what only we need to get the mass of helium-3, okay, which is given by, again, measuring the mass of 1 mole of helium-3, 1 gram, okay, 1 mole, which is we'll get the value, and comparing to 1 mole you get the mass of helium-3 of 1 atom of helium-3 in mass units. Okay, we will see how we can get that later. So we've gotten the mass of the reactants to the left and the mass of the products to the right, of which you have gamma is negligible because it's a radiation, it has no mass. It's a photon, basically. So delta M, which is the mass deficit, is equal to 3.0213. Okay, yeah, that's the real mass of, the reactants. That's the real sum between the mass of the deuterium and the mass of the proton. We subtract from it the mass of 3He, helium-3, which is 3.01608, around that, equal 0.005348 mass unit. Okay, so the energy release is delta M C square, or delta M times 931.494 mega electrovolt. So the energy is 0.005349 around that times 931.494, which is around 4.984 mega electrovolt. Now, I don't round these numbers because in the on the particular level, to get more accurate numbers, it's better not to round any of these numbers. Take them by face value and take multiple digits after each. So now a question would come up. How were we able to figure out the atomic mass of each element, given the difference between the mass of deuterium and H1 combined and that of helium-3, despite the fact that both the reactants and the outcome of this fusion have a total of 2 protons and 1 neutron. So this is interesting that you still have 2 protons and 1 neutron to the right, okay, after the reaction, and still you have 2 different masses. That's why we don't measure the mass of the reactants by summing up the number of protons and neutrons in both atoms. This is the interesting part, okay? Because we cannot get the accurate mass using that method, okay? We need to get the mass of each element apart. Only the mass of H1 is actually the mass of 1 proton because H1 is a proton, all right? So a scientist named Amedeo Avogadro calculated the number of atoms within 1 mole of an atom, and he called it Avogadro's number, all right? So 1 mole of helium-3 weighs around 3.016 grams, and in 1 mole you have, for each atom, in 1 mole you have 6.02214 times 10 to the power 23 atoms for each mole. This is interesting mathematics here, okay? He was able to calculate how many atoms you have in 1 mole of mass, okay? And this is what is called Avogadro's number. So Avogadro's number is 6.02214076 times 10 to the power 23 atoms per mole. 1 mole of helium weighs around 3.016 grams. So the mass per atom is the mass of 1 mole, which is 3.016 grams, divided by the number of Avogadros, divided by the number of atoms to get the mass per 1 atom. And of course, after that, we converted to the atomic mass unit, okay? So 1 mole of helium-3 weighs around 3.016 grams. So the mass of an He3 helium-3 atom would be 3.016 times 10 to the power minus 3, because it's in gram, we need to convert it to kilograms. Divide that by Avogadro's number and you get 5.008 times 10 to the power minus 27 kilograms. Now, 1 unit of mass is 1.66 times 10 to the power minus 27 kilograms. So mass in atomic unit would be 5.008 times 10 to the power minus 27. You divide it by the U value, which is 1.66 10 to the power minus 27 kilograms. Okay, I think that's the mass of the proton, by the way, by which we measure or we take it as a reference for the unit masses. So it gives us around 3.016 units of mass or mass units. All right, going back to the activities of the sun on the sun surface. What are the different activities that it witnesses? What are the different unique features about the sun? So let's at first talk about the sunspot. Now, a sunspot is a dark, cooler area that appears on the photosphere, which is the sun's surface. This is due to intense magnetic activity, okay? And they are dark only relative, of course, to their surrounding, but still extremely hot. This is where you have gases trapped in a region. This is why it darkens that spot relatively to its surrounding areas. The sunspot is actually the result of a strong magnetic field activity suppressing convection, which is it prevents the heat from rising from the core, from below the surface to above the surface. So the heat is trapped in that zone, because normally hot plasma rises from the interior due to the thermofusion reaction. It cools off at the surface. Once it cools off, it loses momentum and falls back to the core due to the gravitational pull of the core. But in sunspots, the magnetic field traps these ionized gases and suppresses convection, okay? And it prevents them to sink back, so they become cooler, much cooler, and apparently darker. That's why they form that dark area that we call a sunspot, okay? So it prevents convection, meaning that these cooler particles, these cooler ionized gases that are supposed to return due to the force of gravity, are trapped because of a strong magnetic field, and they are prevented from going back to the core for some time, okay? So they are trapped due to the magnetic field, and since they are cooler than the surrounding areas, they form what is called a sunspot. Solar flares. Now, technically, a solar flare is a radiation released from the sun's corona, which is the outer ring of the sun, due to the intense magnetic field trapped inside a dark spot. So here, the solar flares are related directly to dark spots. So what happens is that the magnetic field, where you have, these gases trapped within that magnetic field, and that magnetic field is intensifying. Once it becomes strong enough, it bursts out and it carries, it's an explosion of a magnetic field. So it causes a strong radiation bursting out with a spectrum of X-rays, visible light, and radio waves, which are the lower frequencies. This is called the solar flare. The solar flare ejects these gases and ejects these radiations, again, X-rays, visible light bands, and radio waves. And this a huge amount of particles is released, and it's usually tied up with coronal mass ejection, what you call a CME, or coronal mass ejection. How it happens is that due to sun's rotation, okay, the sun's magnetic field is warped and twisted, and it stretches out until it can no longer be held by the core due to the rotation mechanism. So it breaks. There comes a point where it snaps, okay, because the connection from the sunspot to the core has broken due to the rotation movement. So when that virtual magnetic wire, okay, magnetic field snaps, it explosively releases a massive energy, a huge amount of particles and accelerating particles, and radiations, among which we mentioned X-rays, visible light, and radio waves, leading to a solar flare of light and a powerful magnetic wave that is released on Earth, actually, okay, and particles being accelerated. Solar flares fall in different classes. You have A, B, C, that are small minor flares. You have the M class, which is a medium solar flare that can cause radio blackouts. So it affects the communications on the Earth. Why? Because it's a release of an intense electromagnetic field that interferes with satellites and other communication systems. It can even shut down these communication systems. And X class, which is the most dangerous one, very large, very strong, that it causes these, the polar auroras, massive communications shut down, and it can even burn the circuitry of satellites and damage their components, okay? And not only satellites, but even on the surface of the Earth, it can impact the communications. A solar storm is an outburst of radiation and plasma from the sun's atmosphere, leading to magnetic disturbances in space and on the Earth. So it's an outburst of radiation. So when we mentioned, a radiation breaking and the plasma being released from the sun's atmosphere, okay, that's a solar storm leading to magnetic disturbances and usually caused by solar flares. So they are the byproduct of the solar flares, okay? and also coronal mass ejections or CMEs. Also, other solar energetic particle events that might not necessarily fit in these two categories. All right, Sun and Moon distance from the Earth. How can we measure the distance to the Moon from the Earth? First of all, if we consider modern methods to measure the distance between the Earth and the Moon, they are very straightforward and easy to use and pretty accurate, actually. But back in antiquity times, okay, more clever approaches needed to be taken. At first, if we start with modern technologies, modern methods, like via laser ranging, if we send a signal from the Earth to the Moon, it will travel at the speed of light, and by timing the instant the signal was sent and subtracting that from subtracting that from the timestamp when it was received by the receiver, okay, which is next to the transponder, we can find the distance from the surface of the Earth to that of the Moon. The formula is 2 times the distance is equal to the velocity of light times delta t, which is the time difference, okay, from the moment it was sent to the moment it was received. Of course, 2D because the laser is traveling twice the distance from Earth to the Moon back to the Earth, because only on Earth we can measure the time of receiving the signal, okay? We can compare the time of transmission to the time of reception. You don't have like a detector on the Moon itself. So distance is equal velocity times time difference divided by 2. 2D because the signal again is going on a round trip, traveling the distance twice. Delta t is the difference between the time the signal was received and that in which it was sent, giving you how long it took. V is the velocity of light. Now it's not exactly the constant speed of light, because you have a span which is throughout Earth's atmosphere where the speed of light is not actually the constant of the speed of light. It's not actually 3 times 10 to the power 8 meters per second. Given the fact that the atmosphere slows down the speed of light, okay, the speed of the signal. It's not empty space. It has some ambient component, it has gases. That's why throughout the atmosphere, okay, the speed of light would be equal to nu times c. Nu is called the velocity factor. It's actually 1 over epsilon 0 times epsilon r. Epsilon 0 is empty space permittivity, and epsilon r is the relative permittivity of air, okay, depending on the structure of the air. So V equal, at least through the atmosphere, okay, 1 over epsilon 0, epsilon r times c, c being the constant speed of light, if you will. Okay, although light, by the way, is even degrading. It's not exactly a constant, but outside or beyond the Earth's atmosphere, you can consider c, because you've gone beyond the atmosphere at that point. However, you need to average the velocity of speed between these two zones, empty space and the atmospheric region. And by measuring the velocity, okay, or I'm sorry, by calculating the velocity in respect of c throughout the atmosphere, you can get the distance from Earth to the Moon, okay? Of course, the accurate value would be around the equator, if you will, okay? So, distance from the Earth. Now, going back to the classical approach to measure the distance between the Earth and the Moon, Aristarchus, which was a Greek philosopher, scientist, who lived between 230 BC up to 310 BC, used clever methods attempting to estimate the distance from Earth to the Moon during a solar eclipse by estimating the relative size of Earth's shadow and the Moon's path through it. Okay, so he calculated the Moon's distance to be about 20 Earth radii. Okay, he was off by 40 because it's actually 60 radii. We won't get much into that. Okay, and by the way, yeah, also we need to give credit to Galileo, who told us that the Earth was round. Okay, so it's not mentioned in this presentation, so I felt I needed to say that. Okay, Now going back to Aristarchus, so again, he estimated by, if you hold a coin against your eyes and you look, you make the moon block the coin, something like that. Actually, yeah, that's one way to do it. Or measuring the eclipse of the solar eclipse, I think, when the moon blocks the sun. Yeah, this based on the black spot formed on the Earth, if you measure that black spot, he was able to kind of estimate the distance to the moon using that approach. So, classical approach to measure, now here, it's not the distance. What he did is measuring the diameter of the moon in respect to the diameter of the Earth. Now, this was a very clever way to estimate or measure the diameter of the moon. Okay, now given of course that through many people, through scientists traveling back in those days around the Earth, they were able to measure the circumference and estimate the radius or diameter of the Earth. Okay, but how Aristarchus was able to figure out the diameter of the moon in respect of that of the Earth? So during a lunar eclipse, I think. Yeah, during a lunar eclipse, when the Earth sits between the sun and the moon, that's a lunar eclipse. Greek philosopher Aristarchus measured the time it would take the moon to completely plunge in darkness. So, from the moment it starts disappearing until it completely plunges into darkness, he measured that time duration. Okay, and then he kept like counting the time as long as the moon is still plunged in darkness, and then once it started appearing again, okay, and completely emerged, he measured that complete period of time, divided it by the time it took the moon to plunge into darkness, and this is how he got the diameter of the moon in respect of that of the Earth. Okay, I'll try to break it down in more simple terms. So let's read it actually. So Aristarchus measured the time that it would take the moon to completely plunge in darkness from the moment its light starts getting blocked until it's fully dark. So he measured that value. He kept measuring the time during which the moon remained dark until it started gradually becoming lit again and fully emerging from this eclipse. And then he divided that total time by the duration it took to the moon to sink into darkness. Okay, by dividing the full time of darkness by the time of or the duration of the first blackout, he was able to get the diameter of the moon in relationship to that of the Earth. Okay, very clever method. So we divide the full blackout time by the duration it takes the moon to turn black, and how large is the diameter of the Earth relative to the moon's diameter. And we've gotten the diameter of the Earth is equal to 2.5 the diameter of the moon. This is how we've gotten it. Okay, so this is a pretty demonstration, you see. So we measured the time it took. Okay, let me repeat it again. So let's say it took 1 second to completely plunge the moon into darkness, and then 2.5 seconds to completely recover on the other side. Okay, it took it 2.5 seconds for the moon to completely recover from the lunar eclipse. 2.5 divided by 1, as an example, of course, that would give you the diameter of the Earth is 2 times 0.5 the diameter of the moon. Okay, diameter of the Earth is twice 0.5 times the diameter or that of the moon. Measuring the distance from the surface of the Earth to the moon. Okay, another different approach. Using a protractor, we can measure the angle formed between the two edges of a full moon. Okay, from the observer's point of view, we divide this angle. This is like an approximation. We divide this angle by 2, and then by knowing the radius of the moon, we can get the distance to the moon's center. So you have the radius of the moon here, which is half the diameter, okay? You have the angle, right? So you can get the distance to the moon's core, okay? To the center of the moon by using the tangent, okay? The trigonometry, okay? So we divide this angle by 2, which is this area here, and then knowing the radius of the moon, so assuming we have r, the radius, which is half of the diameter, we've gotten that through the measurement of the moon in relationship of diameter of the moon in relationship of that of the Earth. So we can get the distance to the moon's center using trigonometry. Tangent theta is equal to opposite side, which is the radius of the moon, divided by the distance from the surface of the Earth to the core of the moon. Distance all the way to the center. So distance to the center is equal to the radius of the moon times the tangent of theta, and theta being half of the angle that scopes the entire full moon, okay, on the protractor. Measuring the distance from the surface of the Earth to the moon, part 2, if you will. Now we have the distance from the moon to the surface of the Earth. We add the radius of the Earth and we get the orbital radius. So you have the distance from the center of the moon to the surface, and you have the radius of the Earth. If we add both of them, okay, what we get is the orbital radius, which is the distance from the center of the Earth to the center of the moon, which is, by the way, the center of the Earth is the center of the orbit, okay, around the Earth, and the center of the moon, which is very important, okay, to calculate the movement of the moon around the Earth. So let's get the rotation velocity by measuring the orbit's period around the Earth. How can we do that? We can use a clever methodology by measuring, again, by counting on the angle. We measure the angle, okay, from the center of the Earth to both sides of the moon, okay, but here from the center, so you have the radius, then the distance that we've gotten prior to that, okay, so, and yeah, like we use some kind of a window here and an observer where we have the moon on the inside, and we wait for the moon to completely cross that visible window, okay? So given that we have the angle, all right, so we notice that the period it takes, for example, 5 seconds to cross that angle. So how much would it take for the moon to go all around the Earth? So it crossed, let's say, 10 degrees in 5 seconds. Of course, it's a fictitious example. How long would it take it to go around 360 degrees? This is how you get the math. So going back here, so tangent theta equal radius of the moon divided by the radius of the Earth plus the distance to the core, right? So tangent theta equal radius of the moon divided by this entire distance, which is the radius of the Earth plus the distance that we've gotten previously. So the angle, the scope, the angle formed between the moon and the center of the Earth is equal to arctangent, which is the inverse of the tangent of the radius of moon divided by radius of the Earth plus distance to the core. You see, so we multiply theta by 2, which is this angle. Okay, we multiplied by 2 to get the complete angle enclosing the moon, which covers the entire moon in such case. And then by observation, we measure the time it takes the moon to cross this angle opening, if you will, from side to side. So going back, we measure the time it takes for the moon to cross from side to side, okay? So let's consider the time duration is t. The full period of rotation, the full period of the orbit of the moon around the Earth would be what? 360 degrees divided by alpha, which is the full angle, 2 times theta, by the way, here, not theta over 2, 2 times theta, which is this entire angle here. Okay, so the period is 360 divided by the full angle, the full opening, times the period that it takes the moon to cross that angle. Okay, so period equals 360 divided by alpha times t. And this is how we get the period of rotation of the moon around the Earth. Once we have the period of the orbit, and given that we've also calculated the orbital radius, we can obtain the mass of the Earth using Kepler's law. The mass of the planet is equal to 4 pi square r to the power of 3, which is the radius of the orbit, divided by gp, with g being, of course, the gravitational constant, and p the period of the orbit, period of rotation of the moon around the Earth. Okay, so let's get the orbital velocity without using the Earth's mass. You have distance is equal to velocity multiplied by the period of rotation. Distance is the circumference of the orbit, which is 2 pi r0 is equal to velocity multiplied by the period. R0, of course, is the radius of the orbit again, which is the distance from the center of the central planet or the Earth to the center of the moon. So V is equal to 2 pi r0 divided by P, which is the orbital period. All right? We're considering the fact that the trajectory of the moon around Earth is circular, meaning that the orbital velocity, of course, is stable, which leads to Newton's second law called mechanical equilibrium, which states that the sum of all forces is equal to 0 because sigma f is equal to ma, and a, or the acceleration, is 0, is null. So we have a constant speed. Here we have two main forces. Again, the centripetal force, which is the gravitational force, acting against the moon. Okay, it depends on the mass of the moon and that of the Earth as well, pulling the moon inwardly to the Earth's center, and the centrifugal force Fc created by the rotation movement. Let's get the gravitational force. F equals g times lowercase m, which is the mass of the moon in kilograms, capital case M, mass of the Earth in kilograms, radius divided by radius square. The radius, of course, r0 is in meters, and g is the constant of gravity expressed in the lower right corner within this page. So since the moon is in equilibrium, as we mentioned, sigma f is equal to ma equals 0 because there's no acceleration. We've got an f. Now the centrifugal force has the mass of the moon within its components, within its formula, its rotation velocity, and the orbit radius from which we can get the mass. So you have gotten the gravitational force, which is equal to the centrifugal force. So capital F is equal to lowercase f equal to small m v squared over r0. Now we have the velocity, we have the radius, so we can get the mass of the moon, which is equal to capital F, the gravitational force, formerly or previously calculated, multiplied by r0, the radius of rotation, okay, radius of the orbit, divided by the velocity, orbital velocity squared. All right, now let's talk about stars, their life cycle, and stellar evolution. At first, the birthplace of a star is what is called a nebula, which is a massive cloud carrying gas and dust and roaming in space. The nebula, again, is a cloud formed of gas and dust, considered to be the nest from which stars are birthed. And also, it is the remnant of former stars that have died, remnant of dying stars. The nebula, AE, which is the plural of a nebula, are also the building blocks of galaxies. Now let's check the chemical composition of a nebula. A nebula is an interstellar cloud formed primarily of hydrogen, H2, which is the most prevalent element, helium, that comes in second in the chemical structure. You have smaller amount of heavier elements such as carbon, oxygen, nitrogen and other different types of gases. And you have also some amount of dust particles as well. But mainly what you would have is the hydrogen component. And of course, the helium. You can say that hydrogen and helium, which are some of the forms of atoms, are the building blocks of the entire cosmic universe as we know it. All right, so types of nebula. All right, so we have different types of nebula. First type is the emission nebula, which glows due to ionized gas, especially hydrogen, after being stirred and heated up by neighboring stars. So these neighboring stars, when they heat up and stir gases within a nebula, these gases are ionized, they release photons while their electrons get excited and the ground state to a higher state. So as these electrons change their energy levels, okay, and then they fall back to the ground state, they release photons, which is why the nebula seems to be lit, okay? And that's why it's called an emission nebula, because it radiates with the light due to being actually lit or due to being exposed to light by other stars, okay? So it emits light in specific wavelengths, often red, because other wavelengths get absorbed or blocked within the cloud of dust. As an example, you have Orion's nebula, M42. Second, reflective or reflection nebula. Now, reflection nebula doesn't emit light from itself, but rather scatters and reflects the light that it receives from other neighboring stars, and they usually appear blue. So what happens is that it's not through ionization, but it's through reflection via the dust particles that are present within, in high concentration perhaps, within the reflection nebula. These dust particles reflect the light of neighboring stars. Example, the nebula around the Pleiades. All right. 3. Dark nebulas or nebula AE. These are dense clouds of gas and dust. So they block any source of light from the stars and the other nebula behind them. That's why they appear as dark, okay? Because they block the light. They have a high concentration, like a thick layer of dust. All right, so they form some kind of a dark curtain against brighter backgrounds. As an example, you have the Horsehead Nebula. 4. Planetary nebula, formed when a dying low-mass star expels its outer layer. So this is one of the remnants of dying stars, okay? So when a star dies, it releases its expels its outer layers formed of gases and lower mass particles, okay? This creates a glowing shell of gas around a white dwarf, which is the last phase of a small star. As an example, you have the ring nebula M57. Now, the fifth kind, you have supernova remnants, which are the leftover debris of massive or supergiant star explosions. Explosions of stars that are of much massive structure. They are much heavier than the mid-sized stars. All right? So they don't produce a white dwarf in such case. Now, the leftover debris of a massive star explosion will form the remnants of a supernova, which the intense explosion of the star, okay, which is a massive size star. This explosion actually will release, for the remnants, they will have a rich density, or they will be rich in heavy elements and high energy radiation. Example, Carb Nebula M1. Now let's talk about the life cycle of a star. At first, you have stellar nebula, which is the nest or the birthing place of a star. Now here, as we mentioned before, the stellar nebula is made of components such as gases and dust gathered together in a larger cloud. And as the gravity starts pulling different components, different substances, and piling up gases and dust together, it starts forming what is called a protostar, which has a hot, dense core. Okay, gradually but surely it forms, or it leads eventually to what is called a protostar. Now again, what is a protostar? As gravity pulls in more material, because the gravity will start growing as the mass of the piled up materials starts increasing. So as gravity pulls in more surrounding substances such as dust and gas particles, the core heats up. Once the core temperature reaches 10 million kelvins, nuclear fusion starts, which means that hydrogen atoms fuse into helium, right? Into deuterium, actually, at first. Yeah, and you have like two H1 fusing into H2, then H2 to H3, helium-3, helium-4, which is the heaviest material for larger stars. So once the fusion stabilizes, the protostar becomes a main sequence star, which is where the star would spend most of its lifetime. Okay, on the HR diagram, not the Venn diagram, by the way. All right, so this is where the sun is, by the way, in the main sequence cycle or phase of the cycle. 3. Main sequence star. Most of a star's lifetime is in this place, burning hydrogen into helium like the sun. The star is in what we call a hydrostatic equilibrium, where you have the gravity of the core pulling in different gases and fusing them. Now, whenever the fusion occurs, the radiation and the heat would expel or would push the material or the gases outwards. Okay, heated gases and heated atoms and radiation would push outwardly, while the gravity would pull inwardly, making or leading to that equilibrium, what we call hydrostatic equilibrium. This is why the star or the sun is kept as its current form. It's like a reactive cycle, an engine where each time you have a fusion, okay, the fusion would expel gases to the outer layer of the star or the sun, which is, the photosphere. Then once these gases cool down, they are pulled back by the gravity to participate in the reaction. Of course, the heavier materials such as the helium-3 would fuse into gradually into iron, right? Okay, especially for larger massive stars. So higher mass stars will have a more dramatic life cycle later, which we will talk about. Now, let's talk about red giant or supergiant. We have two types. Okay, the red giants are usually the stars that have moderate sizes, okay, relative to the supergiant for much massive, much heavier stars. All right, so once the hydrogen in its core is depleted, the fusion slows down. Okay, so the number, if you will, of fusion reactions taking place in the core would gradually slow down. As a result for that, the gravitational force starts overcoming the outward force pushing outward, okay, which is created by the fusion process. The core starts collapsing on its own gravitational pull and heats up, creating a gap that allows outer layers to expand further due to their gradual detachment from the core surface. Now, let me explain that. So, as a result for the gravitational force starting to overcome the fusion, okay, the core will start contracting even more and shrinking inwardly, okay, contracting upon itself. So most of the heavy materials will start being more concentrated in the core region. This will lower the distance from the outer skin of the core and the gases that are surrounding that region, okay, that are within that are close to the corona, that are within the photosphere, etc. So since the gravitation has become more concentrated around the center of the sun, okay, and since because of that shrinking, the gases that are in the outer layers, okay, such as the photosphere, the convection zone, etc., will expand further, detaching from the core because they are being more liberated from the gravitational pull. All right? So the star becomes what is called a red giant. Red because there's no longer any more combustion, because the fusion processes have become much slower and much much lesser. Okay, so actually the surface of the sun in such case, or the star, has become colder. That's why it becomes more red. Okay, it has cooled down. The star becomes a red giant for low mass stars and supergiant in the case of high mass stars. So fusion of helium and heavier elements start occurring for massive stars, okay, which will eventually, start forming iron cores, much heavier cores. So let's consider the case of low mass stars like the sun, okay. They will transform into planetary nebula and white dwarf, okay. So what happens is that the outer layers get eventually expelled and shed from the atmosphere, because they have become much further distant from the core itself. So that outer layer, or these outer layers, they form a planetary nebula, commonly known as stardust. By the way, they become the new nebula, a new nest for a new star to be forming, okay, as these remnants start attracting surrounding gases released from other also dying stars. The hot core left behind is called a white dwarf. So it is small, dense, and hot due to a still ongoing fusion going down, okay, by the heavier elements, okay, that are still fusing together to that moment, like helium-3 and other heavier components. Okay, so due to that fusion that's still taking place, not as as abundant as it used to be, and for heavier components, actually for heavier atoms, but it's not as hot. It starts gradually cooling down. It eventually cools down, and its glow fades, transforming it into what is called a black dwarf. Okay, just like a lamp that had its fuel completely exhausted. Okay, an oil lamp. Now, for a white dwarf, it's still glowing. This is why we call it a white dwarf. Meanwhile, for highly massive stars, okay, what will happen is that, because here in such case you have a much heavier core with a much higher forces of pressure against that core, okay, so it will eventually explode, leading to a supernova and a one of the two, either a neutron star glowing in the sky, or a black hole, which is a singularity, what we call a singularity, which is a dot-sized point that has an infinite gravity, an infinite density, and it has so much gravity that it pulls even the passing light towards it. Okay, it can swallow up even the light, not only the objects that travel nearby, but also the light. The light is bent down to itself. So fusion continues up to the iron at the core that can no longer release any type of energy in such case. Okay, the iron is the final form in the fusion. The core collapses. All right, it collapses due to the very high pressures, imploding, and then rebounds back. So when it collapses, it rebounds back in a massive outward explosion that we call a supernova. Then, depending on the mass, neutron star, which is extremely dense, made mostly of neutrons, or a black hole, is if the core is much if it's very massive, it will lead to a black hole. A black hole being a singularity, like a ball size matter compressed, the gravity compressing all these substances and matters into that ball, small ball sized not particle but sphere. It has an infinite density and so much gravity. It has such a high gravity that it can even pull light back into itself, preventing it from escaping. And even any other nearby object flying by at a certain threshold, it can be sucked down into that black hole. Actually, black holes cannot be observed by the light going from them because there's no light going from them, okay? The light is completely absorbed, but we can notice or we can identify a black hole based on the objects that are being swallowed down around it, all right? Here we see in this visualization a blue or white dwarf. That's the final stage of a mid-sized star that has a moderate mass that's still hot due to the fusion of heavier elements still going on, okay, but it starts gradually cooling down until it eventually becomes a black dwarf. And finally, the cycle restarts. The remnants of the star forming the nebula give birth to new stars. Once the star dies, the nebula will give birth to newer stars as the gravity of the substances of that nebula will start pulling also other gases around that nebula, pulling more substance, pulling more particles and dust particles, and they start forming a new star as well. Okay, they lead to a core heating up again and reinitiating the fusion process and reinitiating the life cycle of a new star. Let's talk about black holes. So now, the last phase, as we mentioned, after a supernova, a star explosion for highly massive stars is the black hole. Okay, these are even more massive than the ones that eventually become a neutron star. So for the black holes, the core is enormously heavy and its elements start fusing into iron, the heaviest core there is, that no longer releases energy. And it becomes highly massive that it has an unbelievable gravity and an infinite density also. So the heavy iron core keeps compressing, forming an infinitely dense and tiny core, what you call a singularity, with an outstanding gravity that swallows every surrounding object and even light itself. Only objects that are fast enough and travel at a safe distance, this is, by the way, the distance, the circle formed by that distance around the core is called event horizon, but we would get to that. So only objects that are fast enough and traveling at a safe distance from the core can escape being devoured, okay? That distance again is, the circumference around the black hole called event horizon. And once you're past that event horizon, that threshold, you can no longer go back. You are completely swallowed by the black hole. So the perimeter around the black hole, after which a traveling object cannot escape, the gravity is called the event horizon. And the dense core at the center is called the singularity. All right? What is the geometric outlook and structure of a black hole? So at first, as we mentioned, you have the event horizon, which is the boundary around the black hole that once it is crossed, there's no escape from the gravitational pull. You can no longer go back. You are sucked into the midst of the black hole. The singularity is the core itself of the black hole that has been squeezed down due to enormous gravitational forces into an infinitely dense point that has an unbelievable gravity. You have the third thing is the accretion disk. It is hot glowing gas and dust spiraling down into the black hole toward the center, okay? So this is what is called the accretion disk, that zone over here, okay? The gas particles that are being swallowed to the center. And jets are the narrow beams of particles ejected at near light speeds from the disk center, okay? So due to the spiraling gases and particles, these spiraling gases and particles create a current, such as the electrical current would create an electromagnetic wave going around a conductor. The same thing here. Here you have an electromagnetic wave radiation having the same frequency of the circulating current, and it's being ejected to the outside. This is also called Hawking radiation, all right, discovered by Stephen Hawking. So narrow beams of particles ejected at near light speeds from the disk center. The mass of a black hole can range from hundreds to hundreds power the mass of the sun. Theoretically, it can have a miniature, or we can have a miniature atomic mass, okay, in CERN particle accelerator, where they tried to create a black hole in the CERN accelerator, okay, and I believe they had already achieved that. But how are they detected? Now, the bending of light from stars behind them creates, because they have an enormous gravity, okay, the stars that are around the black hole, okay, when we observe them, you see the light bend, okay, and the images that are received from these stars appear to be distorted. This phenomena is called gravitational lensing, which takes the form of distorted light imprints coming from the star. So you have like a light of the star bending here and forming a distorted or stretched shape in the telescope visualizer. All right. So this is one of the clear indicators that since the light has been bent, only a black hole has enough gravitational power to distort and bend the light, forming distorted images of the stars that are lying behind or around that black hole. More than that, X-rays from material in the accretion disk, okay, X-ray ejection is another indicator, and gravitational waves from black holes, mergers, meaning that when you have two galaxies, black holes going against each other, okay, being merged together. You have two black holes on a collision course. What you'll have is, because the matter is circulating at very high speed and it's heavy matter, okay, you have two cores that are very heavy spinning against each other, okay, so they are pulling and releasing against the space fabric, okay. It's like, let me break it down in more simple terms. Imagine that you have the gravitation is a ball going over a fabric like an elastic shirt, okay. So if that ball is rolling back and forth, it will keep pulling the fabric, the shirt, and when it goes further from that shirt, from that spot, okay, like the part of the shirt that was elastically dilating, that were elastically stretched due to the weight of that metal ball, it will retract back to its original form, because the time-space fabric, meaning the cosmos that you see, is like a fabric. Actually, it's like an elastic t-shirt that when you pull against it, okay, it will stretch, but when you release it, it will go back to its original form. So the gravitational waves from black hole mergers, and it will form a ripple, a wave. That is the gravitational wave. So these are ripples in the space-time fabric caused by the acceleration of space objects going around a black hole, okay? So they pull against the surrounding matter, the surrounding planets and stars, and then when they get further, okay, any distortion in the fabric will be released, okay, to its original form, and they keep pushing and pulling. This is what creates a gravitational field. It's similar actually to the waves rippling across a pond of water after a rock hits the water. The same concept. So gravitational waves, simply put, like in a neutron binary star event, okay, or a merger event in which two black holes are colliding against each other, you see, okay, here we have a rotation of two neutron stars, let's say. They spin at a very high velocity, and given that they have a massive weight, they attract the matter around them, okay. As they attract the matter of the space around them, okay, so when they get close to that matter, they pull on the fabric of space, just like, again, you're pulling a t-shirt, all right. So when you get close to that area, you're pulling the t-shirt. Then when you go around, okay, you get further, you're releasing on that pull. So the t-shirt is released, and this is why, yeah, like you create a flapping effect. The matter goes back and forth. This is actually the very definition of the wave, of the gravitational wave. So as matter gets close to the neutron star, okay, it's pulled, then it is released as the neutron star gets further, creating a tidal wave that travels into the time-space fabric, creating a ripple across space. You see here, notice something. This is how it works. It is pulling against the matter around it, but once as it gets further, let me repeat that. You see, it's pulling against the matter, but as it gets further, the matter, the fabric of time-space, restores its original shape, its original placement, if you will. This is how it actually works. Again, just like a ball placed on like a blanket, okay? And as it rolls, it keeps stretching the area where it's rolling, but meanwhile, as it goes further, okay, the area of the blanket that was stretched will restore its original shape. All right. So how can we figure out the speed by which a black hole spins? Now, the rotation speed of a black hole is defined by the formula, which is, it is, at first, you need to get the angular momentum or angular speed. J, or the angular speed, is equal to the inertial moment times the angular velocity, okay? So, J, or angular momentum, is inertia times angular velocity, which is the angular speed, okay? How much degrees you're traveling in terms of time. So another formula for that is the radius times the mass times the tangential velocity. So A, which is the velocity of the speed of the black hole around itself as it's spinning, is equal to J times C, which is the speed of light, divided by G, which is the gravitational constant, times m squared, and of course m is the mass of the black hole itself. All right, so J is the inertial moment times the angular velocity, okay, which is the angular momentum, okay, so angular velocity times inertial moment, Rm, which is the distance time, m, mass times the tangential velocity, and this is where we get the speed of black hole around itself, around its own axis. Let's get the escape velocity, or minimum velocity, required by the object to evade being sucked inside the black hole. So, an object is traveling around the black hole. How much speed does it need so it can escape being pulled into the gravitational force of the singularity? All right, here, and this was, this is actually done by using the laws of energy conservation. So you have two types of energy here. Okay, at first you have the potential energy, which is the energy of the object, okay, due to its altitude from the core center of the black hole, okay. Just like, in physics, you have a potential energy of something that is placed at a high altitude is equal to the mass times the gravity times the height from the ground. All right. So here the potential energy is the force times the height, the distance from the center of gravity. Just like when you have an object again having a certain mass, the force would be the weight, which is mg, times the height from the surface, right? In this case, you have, okay, the gravitational force, not the weight, times the height, which is the distance between the object orbiting around the black hole and the core itself. And of course, here, the core does not have a radius of its own because it's reduced into a singularity, okay? So the surface of the core is the core itself. Okay, they are merged together. So the potential energy is equal to G m, small m, which is the mass of the object, okay, circulating around the core or the black hole, times capital M, which is the mass of the black hole itself, divided by r square, which is the radius of rotation or distance from the core to the object circulating around it, right? Times r, which is the distance from the object to the center of gravity of the core, okay? Or the height, which is the same thing as the radius, right? On the other hand, okay, so that's the first type of energy. On the other hand, you have a kinetic energy that will counterbalance the potential energy. They need to be counterbalanced so that, the object would remain in equilibrium. It won't be sucked into the black hole. Kinetic energy is equal to 1/2 m, which is the mass of the object circulating, times velocity square, velocity of rotation or orbital velocity. Okay, so potential energy gmm over r, kinetic energy 1/2 mv square. Kinetic energy should be equal to the potential energy to achieve that equilibrium so that the object would keep flying around the black hole without risking being swallowed up. So by placing these two equations next to each other, the escape velocity is equal to square root 2gm divided by rs, and rs is called the Schwarzschild radius, which is the distance, the safe distance from the gravitational center, okay, from the core of the black hole. And as long as you are in that safe distance, in such case, you won't risk being completely gobbled up by the black hole. Let's talk right now about the pulsars. So what are the pulsars? Now, why does a black hole or a binary neutron star having two stars rotating around each other produce a radiation? That is a commonly, asked question, and because where does the light come from, or what causes that radiation? So let's take the case of pulsars. A pulsar is actually a neutron star that rotates very rapidly, emitting a beam of electromagnetic radiation, usually radio waves, X-rays, and or gamma rays from its pole. So how does it actually work? How does that emission take place? Now, according to Coulomb's law, a conductor through which passes an electrical current will radiate an electromagnetic field having the same properties, meaning same frequency and same wavelengths, as the electrical current itself. So it will act as an antenna actually, okay? Any conductor having a current running through it will act as an antenna radiating an electromagnetic field having the same wavelengths, the same frequency as the current or the signal, electrical signal going through it. And by the way, the direction of rotation will follow the same pattern of a screwdriver, meaning that if you look here, when you have a circulating current going this way, imagine a screwdriver. It will be cutting inwardly, okay? It will be like going through inwardly in that direction. If the rotation of the current is anti-clockwise, different or opposite to the rotation of the clock, that field would be going the other way around, okay, in the opposite direction. So in other words, the field vectors will rotate clockwise as the current is moving inwardly, okay? Actually, the current will rotate clockwise as the field is moving inwardly, all right? And vice versa, okay? So as the current goes clockwise, the field will be moving inwardly. Of course, we note here that since the electrical current has a low frequency, the electromagnetic waves having that same frequency won't be visible. Why? Because when we talk about electricity, they will be in the range of, radio waves if you have a communication cable, or 60 hertz when you have like high current, okay? You can't see that radiation, okay? It won't be visible. Also, it's there, but you cannot see it. But when we follow the same pattern, okay, the current, which is a flow of electrons around the pulsar, that is generated due to the rapid rotation of ionized gases. Okay, so the star, it's rotating at a very high speed, dragging with it ionized particles and electrons. These will generate a current, okay? And this is my assumption that the frequency of that current would be the same frequency as, or, you know, if we get the period from the frequency of the current, okay, that period would be the same as the period of rotation of the neutron star or the pulsar around itself. Okay, that's just my assumption. So this current is of a high speed and frequency, which I personally believe that it will produce a radiation of the same frequency projecting from the pole of the star. The same frequency of light would be the frequency of electrons, or you know, the current generated by the electrons and ionized gases, you know, rotating around and along with the pulsar. If we evaluate the period of the wavelengths, which is the inverse of the frequency, that the wavelengths that's being radiated, okay, we get the rotation period of the electron. This is what I believe. We get the rotation period of the electron around the center of the star, or the time it takes the electron to complete one full cycle. This is my own perspective. This is my own assumptions here, okay? Meanwhile, the magnetic field gathering around the atmosphere ring will project from the center outwardly, and since it's a high frequency electron, in some instances it falls in the range of visible light. So let's read it again. The magnetic field gathering around the atmospheric ring will project from the center outwardly, and given that it's a high frequency electronic current, if you will, a flow of electrons and ionized gases, in some instances, depends on its proximity and its speed of rotation, it will produce radiation in the visible range. However, you have other ionized particles that are rotating further from the center. They would have smaller periods of rotation, lower speeds, lower frequencies, and thus they would create radio waves. We've seen here among the radiation, you have an X-ray, which is a very high frequency. You have radio waves and visible light, as we mentioned. Now, let's talk about the quasar. Quasar is a supermassive black hole which is feeding or sucking the gases and dust of a nearby star, or perhaps they might be gases and dust of a nearby nebula or a galaxy in general. This will give them more fuel. It will give them extreme brightness and excessive energy. The gas and dust swallowed up will heat due to the friction and the gravitational forces, the ionization and the flowing electrons because of that heating up and ionization of the gases and dust nearby will result in an expulsion of a jet of visible light. Also, you have ultraviolet, you have X-rays, you have visible light. Now you see here, when we talk about ultraviolet light and X-rays, they are of an extremely high frequencies, suggesting that the circulating current of electrons and ionized gases are of an extreme high speed rotation, okay, are rotating at a very high speed, producing that very high frequency. And also the visible light is of a high frequency, but UV is have even much higher frequencies also with X-rays, because they are beyond the visible range. And when we talk about the expulsion or the detection of radio waves, it's because that some particles that are spinning around a quasar or around a neutron star would have a longer orbit. They would be more further from the core, okay, leading to the, you know, slower speed, meaning longer periods, lower frequencies, and okay, eventually they would be more likely producing a radio wave. Let's talk now about the galaxies, and starting with the first galaxy, the most common one that we know, which is the Milky Way, where the solar system exists. So the Milky Way is a spiral galaxy that houses our solar system. The diameter is around 100,000 light years across. A light year is a distance traveled by light during an entire year, by the way. And we measure in terms of light years because it's ridiculous to try to measure with kilometers, okay? Because we're talking about a very, very colossal astronomical distances, okay? Now the thickness, meaning from up to down, if you consider, because the Milky Way is a disk, okay? So the thickness from the lower part of the Milky Way to the upper part, because it's like a flattened disk, you can say, is around 1000 light years. So notice that its breadth or diameter is 100,000 times or 100 times its thickness, okay? Number of stars available or existing in the Milky Way is estimated to be 200 to 400 billion stars. The structure, you have a bulge, that is the spherical area of all the stars around the center. That's the bulge over here. And the disk, okay, which contains these spiral arms around the center, spiral strings, made of younger stars, gas and dust, okay? Now, dust and gases here on the edges being the lightest components, okay? They would, the gravity would have a lower effect on them. That's why they can, sit further from other heavier objects to the center. You have also a halo, which is the spherical cloud of all the stars and globular clusters that are surrounding the disk, okay, around the spherical bulge, and dark matter halo, invisible but adds most of the galaxy's mass. And we will talk further about the bulge. Why is there a bulge? Why is there a disk? Okay, and why it would have like older stars in the bulge and near the center of the galaxy than the younger stars that are sitting in the arms region. All right. Apart from the solar system, the sun and its surrounding planets and moons, the Milky Way has other stars or star clusters. You have nebula, stardust, clouds and gases. You have black holes from former stars that have died. You have neutron stars, exoplanets, which are planets outside of the solar system. Okay, so it's not only the solar system sitting in the Milky Way, of course. You have billions of stars and even solar systems outside of our own solar system. How have we been able to study the Milky Way? Now, one of the properties or one of the ways to detect or to identify what's in the Milky Way, how it's structured, has been analyzing radio waves, analyzing infrared signals, because infrared signals can penetrate much further than, because they are longer waves, okay, they can penetrate much further than shorter waves. So the returned infrared signals can tell us a lot about the structure of the Milky Way. Also other frequencies of the electromagnetic spectrum, counting the stars and tracking their motion, because you can kind of estimate the number of stars. Of course, you would be off by I don't know how much, but taking a specific area in the 360 degrees and trying to estimate how much, how many stars you have, and then, dividing, if you will, the spherical, the space sphere, okay, around the planet, around Earth, okay, which is, you can say 4 pi r squared depending on how much you're taking the r, all right? So you can divide that external surface of the celestial sphere, this is what it's called, dividing it by that area where you've estimated a certain number of stars, you can kind of get to how many stars you have in that Milky Way, okay, that are in the proximity of the Milky Way, not the very distant ones, okay, and also analyzing through ground and space telescopes like Hubble, James Webb, and others. Let's put it in simpler terms. So before a galaxy even forms, you need at first to start with the raw materials. These are the components that form the gas cloud of a nebula, with its dust trapped within that gas cloud, made usually again of methane, ammonia, water vapor, etc. And the nebula, as we mentioned before, it is the birthplace of the first star in the galaxy. So before you get a galaxy, you need to at least get the first star. Okay, you don't go from nebula to galaxy immediately. Once that star completes its life cycle, it either becomes a black dwarf, if it was, a mid-range or mid-size star that was not very massive, or a black hole if it was a supermassive star. Okay, the black hole you will get there from a supergiant, super red giant. Okay, if the star was very massive, which is, by the way, the black hole is like the one you have in the midst of the Milky Way. It will have a powerful gravity that will keep pulling on surrounding gases, dust, and those that are the remnant from other dying stars, along with the residues of its own outer layer that was shed. All right? So these different substances and gases will be revolving around it as surrounding gases and dust. Of course, some of them would be also swallowed by its gravity. As surrounding gases and dust revolving around this black hole clump up, they start forming a protostar, and this core will start heating up till it arrives to a temperature more than 10,000 degrees, which is, necessary to start the fusion process. Once the fusion process starts, it becomes like our sun. The protostar becomes a main sequence star. And after the life cycle is finished, meaning that even after that star itself dies, this newer star that died will also produce residue, expelling its outer layer even further down the line from its core and from the center of the galaxy, that will participate, like these gases and residues, will participate in creating new stars. And this is how the cycle repeats itself as you go further from the galaxy center along the spiral arms. Because the closer you get, okay, to the center, the older the stars would be. Why? Because actually the center is made of the black hole of the oldest star that we have in the system completely. As you go further from the center, okay, newer stars are being formed, and it makes sense because here, due to the large distance, you would have, by the way, um, if you will, like the stars, they would be wrapped up with gases, would be formed by the gases that are much further from the center. Okay, it will form from lower metals, and they would be new stars. Okay, from lower, actually not metals, they would form from protons that are available on that distance. But meanwhile, as you get closer, you have heavier materials that were generated by older stars that had died out. Okay? Okay, so how did the galaxies form and the universe begin? Okay, so let's approach the biblical perspective. It's interesting in the book of Genesis in the Bible how it portrays the creation of the universe, the cosmic universe. By the way, cosmic means it was created. So if you go to the first verse, in the beginning, God, Elohim, the God of the Bible, created, and this is interesting here. This is the amplified version of the Bible. He created by forming from nothing the heavens and the earth. From nothing, okay? So when you say everything came from nothing, yes, that's correct. Okay, however, you need a catalyst and you need a creator. It cannot just form on its own without a God doing that, without an external active agent, so to speak, to activate that process. So at first, when we refer to the beginning, space has a beginning, the beginning of space and time. And by the way, space and time, these two terms are correlated. That's the starting point that initiated the creation of the time-space fabric. Okay? And by the way, there are clues about the time-space fabric in the Bible also, which describe exactly that the created universe is actually just like a garment, okay? Or a fabric, another word for fabric, that can be elastically distorted by gravity, that can be affected through, it's mainly when you affect the space, you can affect the time because these two are correlated. So it came from nothing, but God alone creates something out of nothing, okay? Through my personal belief at least. and every reaction needs a catalyzer. It cannot start on its own. Okay? So, another verse in Hebrews 11:3, it says that we understand that the world's universe ages were framed and created, so formed and put in order and equipped for their intended purpose, which are, the equipping means they were given the laws of physics, okay, to work out their intended purpose by the word of God. By the word of God. Another name for the word of God is Jesus. Also, the word of God, you can take it also. That's the other layer of the meaning, is the frequency of God, the spoken word, because every type of matter has a frequency to it. So that what is seen was not made out of the things which are visible. Okay, what is seen is made of energy that is not visible. This is also has been scientifically proven. That's Hebrews 11:3. Now, by the words here, the scripture is referring to a multiverse, and another controversial subject. Okay, now this is just me, okay, trying to interpret, but I believe that it's referring to a multiple dimension universe. The second important evidence is the part stating what is seen was not made of things visible, which makes the case for energy and heat transforming into visible matter. Okay, you had energy and heat that were not visible. After, you see, the heat, when it got to a point that it crossed the threshold of visible light, this is when we started observing. Okay, we start observing what's happening. So the universe and ages represent respectively space and time, or space-time fabric, and it states that they were formed by the word of God, who is Jesus Christ. Now the world also represents sound. The word also represents sound vibrations and frequencies, and it has been proven that every type of matter has its own frequency, by the way. Every element on the periodic table has its own frequency. This you can test a little bit that when you tap on the metal, you have a different type of sound, type of frequency produced versus when you tap on the rock. Each type of matter has a specific sound, a specific frequency for it. Now, you can make the case that the metals or the substance produces a sound frequency, but also you can reverse that because the energy is transferable. The energy actually can be converted from one type to another. So I would also stand on the argument that the frequency itself has made these things that are metals. So they were created by a sound frequency. Okay, this is the power of the mouse. When you say something, you can speak your future into existence. Okay. Even the witchcraft people believe that, but I'm a believer in Jesus Christ. When you do it through Jesus, by the power of the name of Jesus, you can create something. You can change your own future, because the tongue is like a rudder that can steer your entire life. Okay, of course, now that's another subject. So another verse, Psalm 33 verse 8 to 9. Let all the earth fear and worship the Lord. Let all the inhabitants of the world stand in awe of him, For he spoke and it was done. Notice, he commanded and it stood fast. So he spoke everything into existence and into order. That's another verse showing that everything created, whether galaxies, stars, planets, moons, were created by a spoken word from God, sound frequencies, okay, that dictated the physical laws of the universe and everything in that universe, everything in it as well. Also in Isaiah 40, chapter 40 verse 22. It is God who sits above the circle or the horizon of the earth, and its inhabitants are like grasshoppers, like relatively in size. we're saying. It is he who stretches. That's interesting. It is he who stretches out the heavens like gauze, like curtains. Another word for that, tent or thin clothes, and spreads them out like a tent to dwell in. Wow. Now, he who stretches out the heavens, that part. The heavens refers to multiple dimensions, okay? Among them, the atmosphere also implies, okay? The act of stretching out is what was discovered by Hubble's telescope on the expanding universe, by the way, which stretches uniformly like a garment, okay, or an elastic clothing. If you imagine a t-shirt that has different multicolored dots painted on it, okay, and you stretch it in a specific direction by 5 centimeters, you will notice that it's not only the edge that will stretch more than the first the edge, it won't like stretch more than the center. No, it will all uniformly stretch, meaning that the gap between every two consecutive dots will increase by 5 centimeters from the center all the way down along the entire cloth, which is the same characteristic of a garment or a fabric or a t-shirt, which became, by the way, known as Hubble's law. But interestingly, it was already mentioned thousands of years ago in the Bible. Formation dynamics. In secular science, now it's believed, that everything in the universe started from a singularity, a highly dense point, just like the final phase of a supernova. That point had an infinite density. It then exploded into what is known as the Big Bang, releasing an enormous amount of energy and heat with dense plasma. The denser regions started attracting more matter through gravity, becoming, the birthing place of stars and galaxies, which are the nebulas, by the way. Also, it's believed that you have what's called dark matter, okay, an invisible matter that has a tangible effect, tangible energy, and the effect on the gravity, okay. It's a dominant component of matter that also started assembling under gravity, and this grouping of dark matter became gravitational wells, pulling other matter, the other the known types of matter within them, okay. So why is called dark matter? Because it's not like detectable, it's not tangible, but still it still have an effect on gravity. It has its own gravitational pull. So hydrogen and helium, that were the main elements created during that Big Bang, started falling into these gravitational wells, started clumping up and gathering. And these gravitational wells are also called halos. As these gases cooled down, they started contracting and fragmenting, fusing into the first stars, okay? This is where you start having the protostars, and then the fusion process led to the first main sequence stars, okay? And a lot of that, by the way, is scientific. Now, of course, it's hard to I don't know exactly. The dark matter is still theoretical. We don't completely understand it. Okay, but from the Bible perspective, it's interesting that, okay, you have in Genesis chapter 1, verse 3, and God said, "Let there be light," and there was light. So God spoke light into existence. Technically speaking, God through sound frequencies created everything, and he created light through that frequency. Again, any type of energy is convertible. It can be converted from one form to another, just like you have a sound frequency can become mechanical. So energy is transferable between different types of media, okay? It can the electrical power can become mechanical and vice versa. Genesis 1, chapter 1, 1, verse 7 to 8. And God made the expanse of the sky and separated the waters which were under the expanse from the water which were above the expanse. Okay, water under the expanse, so you have the ocean waters beneath and the waters that are above which are the sky or the atmosphere in heaven. All right, it's portrayed over here. Like, it's interesting that it is portrayed within this verse. So the Earth's substance for dust and other particles were already created, and they were afterwards covered entirely by water. Then God spoke and separated that water between water, above in the atmosphere and water below, which is below the sky or covering, the oceans. Okay. Then God said, let the waters below the heavens be gathered into one place of standing, pooling together, and let the dry land appear. So there was no dry land at first. It was entirely covered, the earth was entirely covered with water. The water receded in one place and dry land appeared. It's interesting that you had no dry land. You had a pile of dust, if you will, and rocks, but it was completely covered in water. So water separated afterwards. And God said, let there be light, and there was light. Genesis chapter 1:3. So he spoke light into existence. Through, again, the sound, the power of sound waves, that energy created light. So God said, let the earth sprout tender vegetation. Here, the first forms of life, mainly the vegetation, which is important to come out first because it's self-producing, it can reproduce itself, plus it becomes, the food and the provision for other animals that will come after. And anything, all the fruit trees bearing fruit according to or limited to consistent with their kind, meaning that apples cannot produce oranges. Each reproduces after its own kind. Okay, that's also an important connotation by design. So, whose seed is in them upon the earth. So the seed are within themselves, within the same plants. They produce the seed, they throw it down, and they recreate themselves. And it was so. That's Genesis 1:11, the amplified version. The first forms of primordial lives of seeds and vegetation appeared at that point, but the stars were not created yet. Then God, so Genesis chapter 1, verse 14, then God said, let there be light bearers, sun, moon, stars in the expanse of the heavens to separate the day from the night, and let them be useful for signs, tokens of God's providential care, and for marking seasons, days, and years. So, in this phase, the sun was formed, the moon, the stars were created, and in the part where it said, let them be useful as a token for seasons, days, and years, indeed, time has been measured according to the revolution of the sun, the moon, but also considering star constellations. In antiquity, actually, this is what they used to do. They used the constellations as markers. So when a constellation sits above a megalithic structure, for instance, they knew that it will be realigned again after 5,000 years, 2,000 years, based on what constellation we are referring to. So constellations will line up above a particular geolocation on Earth every certain number of thousand years. Verse 21, so God created the great sea monsters. Now that's interesting, okay, just like Loch Ness. It's not only referring to the creation of whales and sharks, but great sea monsters, and every living creature that moves, with which the waters swarmed according to their kind, and every winged bird according to its kind. So after the creation of moons and stars, the fish and other life forms that move within the waters were created. Along with the birds, it's interesting, he's referring to sea monsters. It's not just normal whales, it's something much bigger than that. Like the Cryptoclydus, Elasmosaurus, these type of water dinosaurs that you might be familiar with. Among them, what has been, known lately as the monster of Loch Ness during the past 2 decades at least. Verse 24, then God said, let the earth bring forth living creatures according to, limited to, consistent with, again, their kind. So livestock, crawling things, and wild animals of the earth according to their kinds. And it was so because he had spoken them into creation. He had spoken them. They didn't come out of nothing. He spoken them into existence. Now, at this phase of creation, animal life on Earth comes forth after the Earth became ready with vegetation and seed required to sustain them. That's important. It's interesting that the verse keeps repeating the verbiage limited to consistent with their kind. The reason for that is, unlike the mainstream idea of different life forms evolving from one cell, one organism, by design, each species reproduces after its own kind. So dogs give birth to dogs, cats to cats. Now, what is the argument behind that? So you would ask, how do you explain 100 types of dogs, of frogs? Where did that diversity actually come from, right? And the answer lies in the area of the genetics. Okay, so the thing is, different types of multicolored frogs, different types of birds, all of these came from the same ancestor, from one prototype that carried already all the DNA information needed to produce a variety of frogs and dogs and birds. Frogs, for example, have diverse sizes, varied shapes, different skin pigmentation and skin chemical characteristics. Some are poisonous, others are not, but the DNA sequences were already available in the parent. Although some of these traits are expressed, others remain genetically recessive in the parent. Okay, so simply, just like you would have a gene code for blonde hair, for red hair, okay, some specific physical traits for us, people. So most of these might remain recessive until a specific generation, okay, concealed. Recessive and concealed means that they are still in the genetic pool, okay, but they are not expressed physically on the outside. So you might have the blonde gene within you, but you have a colored hair. However, your kid in the future might be born with a blonde hair, okay? And this is usually, the result of that gene manifesting in that next generation. So within our DNA sequences, you have some hereditary traits that are recessive, okay, and concealed, but in later generations, it would likely show up in one of the children, just like being left-handed, okay? So one of the kids would suddenly appear left-handed, although the parents are right-handed, okay? So the answer is in the genetics. Also, you might get a red-headed child, although, all of your parents were black-haired, okay? And also, like, perhaps one of your ancestors back in the generations had a red hair, okay? But it took that time for it to manifest, okay? Let's back up a little bit. So the space-time fabric and dimensions were created first, then after it, the original substance of matter like dust particles and water, then light was spoken into existence by God. In other words, through frequency and vibration, light came to existence, which is another word for energy and radiation. Light is an electromagnetic wave, by the way. It's a wave, it's an energy, okay? It carries energy, and it's a radiation, okay? It has electrical field, it has power within it, it carries energy, all of that. And through it, matter was being transformed, conforming to Einstein's theory of E equal mc squared. Because according to Einstein, you have the mass can be converted to light and vice versa, okay? And that process will produce energy, of course. And it requires energy to transfer from one state of mass, to a state of energy, to a state of light, or vice versa, right? So I hope I did not confuse everything here. So stating that energy can transform into matter and vice versa. Now, gravitational forces Actually, when you melt something under high temperature, you're converting, matter to energy. That's one simple example. So gravitational forces started acting between different particles and gases, leading them to condense together. Hydrogen and helium assembled together, and as the gravitational forces increased, the assembled core heated up, eventually leading to the fusion process to form stars. Massive superstars then that exploded in the latter phase of their life cycle, each led to a black hole, attracting to it other stars and stellar objects, some sucked into its core, others circulating around it, leading to the formation of galaxies. And of course, you have different types of galaxies. It's not only the spiral ones, okay? You have other types of galaxies as well. Creation dynamics or formation dynamics of the created universe, the Bible perspective. As for the planetary system forming around stars like the solar system, the matter circulating fast enough around the central star, which is the sun in our case, managed to escape being swallowed up and started piling up into more condensed composites. The heavier materials made of metals and dust rotated closer to the central star due to gravity. Having a greater mass, they become subject to a greater gravitational pull closer to the star, which is governed by the equation F equals G M divided by R squared. Small m is the mass of the pile, big M is the mass of the sun. As they pile up together, they become even heavier, attracting more materials such as dust and some gases, forming heavy and extremely hot planets due to their proximity to the star, to the sun, like Mercury and Mars, and even the Earth, although the Earth has a more moderate temperature due to its atmosphere. The lighter materials, made mainly of water, gases, and some dust particles, will be less subject to the forces of gravity, making their centrifugal velocity then more dominant. This will allow them to circulate around the star at a further distance. Gradually, due to their gravitational forces, they start piling up, forming mainly gas planets. Most gas composites will freeze due to their distance from the sun as they gather under pressure, mainly due to their far distance, as we mentioned, from the central sun. As their assembled weight becomes heavier, they attract heavier objects like dust, like rocks, and of course the rocks and dust will be pulled further inside the core, and maybe some small concentration of metals. Types of galaxies. We have at first spiral galaxies containing older stars around the center, which is around the bulge. Younger stars that are hot blue in the arms because they are younger, they are hotter, have higher temperatures. Stars in formation process in gas and dust-rich regions. Bad spiral galaxies, of which the Milky Way is considered barred, similar to spiral galaxies, but have an elongated bar shape extending from the bulge, okay? Like they are stretched in one direction. Stars and gas are funneled through the bar, possibly triggering more star formation. Elliptical galaxies, nearly spherical, like E0 galaxy, or tightly elongated, E7, mostly made of old stars, like red stars. Stars move in random orbits, range from dwarf elliptical to giant ellipticals. Lenticular galaxies, S0, which they are hybrid between spiral and elliptical, appear often as faded spirals, okay? Like they are fading, having used up their fuel, their gases. Finally, you have irregular galaxies. There's no defined shape or structure, mainly made of gas, dust, and young stars, usually resulting from galactic collisions, okay, between two galaxies. Factors that determine their shape, so galaxies having a high density of gases, dust, and other materials are more likely to be spiral galaxies due to the gravitational pull and the rotation mechanism, in case they have older stars that gather in the bulge region, which attract more material, and that material will start rotating around the central bulge. Okay, and enough material to form younger stars from the remnant of dead stars and ambient materials as we move further from the center. So as we move further from the center, you are more likely to have younger stars. All right, but it has enough fuel that the rotation motion is very active. Meanwhile, as more stars and gases are funneled through, they become elongated, forming the bar-shaped spiral galaxies. So they start dying, okay? While star formation frequency remains high, even for galaxies, barred spiral galaxies. When gas and dust start getting exhausted, fewer stars are formed, and most remaining stars will be mostly old, gathering mostly in the bulge area, okay? But the other, like the spiral areas, okay, will start dying out. Stars will move in a random orbit, and the galaxy shape becomes more elliptical or elongated. As the concentration of gas and dust gets even lower, star formation will decrease even more, and the galaxy becomes disc-like shaped, okay? It becomes more and more irregular because there's not much more going on, okay? And the rotation motion, the formation of new stars has dimmed out. For the last type, they start becoming more and more irregular, okay? For the last type of galaxies, which is the irregular one, there's no defined shape for it, okay? And it has younger stars enlarged that started forming due to the galaxy attracting gases and other particles released from a recent supernova nearby. So these irregular galaxies can be the remnant of a dying star, and it has some gases, some other particles, and new stars have started forming. So the gravitational forces are still weak to form a definitive shape, all right? So it's an amount of mass of gases and particles where young stars are forming, and there's no like central gravity that's more dominant to pull other materials in to start the spiral motion around a central axis. That's why it is irregular, because there is a uniformity in some direction in the mass of gases and dust, and there's some formation of new stars that has started to take place. Okay, probably a part of the galaxy had a white dwarf, all right, and it has released its outer layers, its outer shell, so not much is going on. Astronomy equations and measurements, measuring the distance to a star. So how do we measure the distance from Earth to the star? At first, okay, so what we found out is measuring the distance, we use the parallax angle. What is the parallax? The parallax is the apparent shift in the position of a star or any other stellar object against a distant background when observed from two different locations on Earth. This is like holding a pebble in your finger, closing the left eye, looking at the pebble, then switching to the right eye, closing the right eye, okay, and looking to the pebble from the left eye. You will notice that the pebble shifts in its relative position, right? So when we close the right eye, it is on the left. When we close the left eye and look at the right eye, it shifts to the right, okay? This is called the parallax. So the parallax actually is the angle between the two positions from your vantage point. This is what we call the parallax. The angle is measured in arc seconds, meaning that's 3,600 degrees, okay? Because the shift is very small, that's why we use the arc second. So the angle is measured in arc seconds and the distance in parsec. 1 parsec is when a star will shift in 1 arc second after the Earth moves 1 astronomical unit, okay? That's the parsec. It is when a star moves 1 arc second, which is 3,600 degrees, or 0.00028 degrees, when the Earth moves in 1 astronomical a distance of 1 astronomical unit. 1 one astronomical unit actually is the distance from Earth to the Sun. This is 1 AU. That's the distance from the Earth to the Sun. So again, one full circle, as we know, is 360 degrees. 1 degree is 60 arc minutes. So we're dividing 1 degree over 60 in a minute. It's 60 arc minutes. 1 arc minute will give us also 60 arc seconds, as if treating 1 degree like an hour made of 3,600 seconds. So 1 arc second is equal to 1 over 3,600 degrees, which is 0.00028 degrees. The distance in parsecs, by the way, 1 parsec is around 326 times 10 to the power minus 2, or 3.26 light years. All right, so the distance to the star is 1 over p, p being the parallax angle in arc seconds, d again measured in parsecs. 1 parsec is around 3.26 light years. A light year, speaking of which, is the distance traveled by light in one entire year, because we are talking about astronomical ranges of distance. Okay, we cannot measure them in kilometers, it's ridiculous. So as we see here, let's say we're looking to the star from 2 vantage points. The star will shift from this position, let's say, to this position, okay, against a stable background. So as we noted that, okay, this is the angle that we measure in arc seconds. We get the inverse of the angle, the parallax, and from that we deduce the distance to the star again in parsecs. 1 parsec being 3.26 light years. Again, a parsec is when a star will shift, the distance in parsec is when a star will shift 1 arc second after the Earth moves around the Sun 1 astronomical unit. Also, another formula relating to the distance is apparent versus absolute magnitude. Okay, small m being the apparent magnitude or brightness. How bright does the star appear from the Earth? This is the apparent magnitude. Capital M is the absolute magnitude, or how bright it would appear at 10 parsecs of distance. All right, so small m is the apparent magnitude or brightness. How bright does the star appear from the Earth? Capital M is the absolute magnitude, how bright it would appear at a distance of 10 parsecs. So small m, lowercase m, minus big M equal 5 log, it's a log scale, equal 5 log base 10, the distance in parsecs, minus 5. So d is equal, so we elevate the left and the right by 10 to the power of these elements, okay? So d would be 10 to the power of small m minus big M plus 5 over 5. Here's how we got that. Okay, small m minus capital M equal 5 log base 10 d, which is the distance, minus 5. Log base 10, the distance, is equal m minus 5 plus 5 divided by 5. So 10 to the power of log base 10 d equal 10 to the power of m minus m plus 5 divided by 5. 10 log base 10 d is d, okay? That's the logarithm. So d equal 10 to the power of small m minus big M plus 5 divided by 5. All right? Usually, we have the distance, we can measure the absolute magnitude, okay? So these are interchangeable. So again, small m, the apparent magnitude or brightness, is how bright does the star appear from the Earth. We measure it it is related to the flux, okay? And big M is the absolute magnitude, how bright it would appear at a distance of 10 parsecs. Let's say it is from 10 parsecs to our vantage point. To measure the apparent magnitude M, we use a photoreceptor or a CCD cam on a telescope. We detect the amount of flux. Flux is the light energy. It's the power of light, okay, in meter square area. So we detect the amount of flux or light energy that's being received from the star by the device. Then the brightness is converted to a logarithmic magnitude scale, As an example, Sirius is minus 1.46 because on the logarithmic scale, even many negative values are on the log are positive in power. So usually you would have already calculated the distance and you use that to get the absolute magnitude, which is the brightness of a light at 10 parsecs. Again, we have this formula over here. All right, so as a reminder, the apparent magnitude is actually measured by detecting the amount of flux, which is the light energy, in watts per meter square, which is the surface, spherical surface of the star, which is 4 pi r square. Measuring the distance to a star using luminosity. First, let's figure out how to get the temperature of a star. It will come in handy in a moment. It will be useful in a moment. In 1900, physicist Max Planck was able to find how to measure a body's temperature based on its wavelengths or color, and temperature value was found by establishing the relationship between the brightness value of that wavelength and the wavelength itself, okay, as it changes on a curve. It has a curvature to it. The curve is called Planck Blackbody's curve. All right. So let's observe this picture here from the spacemath.nasa. If you notice that if you have the wavelength and if you have the the temperature, because we know the temperature of the wavelengths, all right, but I need the exact value of wavelengths, and to get the temperature I need to get the luminosity, okay, and this is how I establish actually I do have the temperature, okay, but I can get the luminosity from the temperature itself. All right, so if we look at the red wavelengths, you notice that the red wavelengths, okay, will need to have a much higher luminosity to get to 5500 degrees Kelvin. Compared to the green wavelengths, for a lower luminosity, it can be as hot. And as you go down, for shorter wavelengths, have higher temperatures, even with lower luminosity, which is a lower condensation of light, okay? In other words, to put it simply, shorter wavelengths are much hotter than longer wavelengths. Or in other words, higher frequencies are much hotter than lower frequencies. So again, let's check the temperature. So the temperature, at first, yeah, we need to get the temperature from lambda or vice versa, but usually we know the temperature from the color. So to put it simply, okay, at first, temperature at Kelvin is temperature in Celsius plus 273. The temperature is 289,700, okay, or if you will, 2,897,000 kelvins divided by lambda in nanometers. Lambda needs to be expressed in nanometers. And this is how you get the temperature of a star. Or if we flip them, so lambda max, the relationship between the wavelengths and the temperature in Kelvin is lambda max in meters is 2.898 times 10 to the power minus 3 divided by the temperature in Kelvin, because here it's expressed in meter, here in nanometers. All right. Observing the chart, we notice that the higher frequencies, which are these ones here, okay, the blue, navy, the green are higher frequencies than the red. So higher frequencies or shorter wavelengths present higher temperatures at lower brightness. In other words, smaller stars that are in the blue range are much hotter than their peers having a red color. Okay, it's related to wavelengths, the frequency. Of course, even for a lower frequency, red giants are hot. Why? Because they are giant. They have too much flux going, okay, they have too much area. So since they are bigger, they will emit as much temperature as the smallest one. But in a nutshell, shorter wavelengths and higher frequencies are much hotter than longer wavelengths and lower frequencies. Okay? On the other hand, stars with longer waves, lower frequency in the red range, will need to be much brighter, of a large size like the red supergiants, to be as hot as the blue small ones. To give a comparison in nature, and this is where you completely get it and becomes much simpler and much easier to understand for the ones that are not familiar with that concept. To give a comparison in nature, when you burn wood, their fire color would be yellow to reddish, and it's a cooler flame with an incomplete combustion. Why? Because there's too much CO2 going on. It's not a complete combustion, so that you can pass your hand through it without getting burned. Sorry for the typos over here, by the way. Okay, why? Because it's not as hot as you would expect. But on the other hand, burning methane will display a blue torch with a complete combustion. Nothing is left from that combustion, okay, from that burning. It will have a complete combustion feature, burning much hotter than passing your hand through it for the same time that you passed your hand through the fire of wood, would result to or would lead to serious injuries, because it is much hotter than burning wood. Using the star luminosity, Einar Hertzsprung, which is Danish, and Henry Norris Russell, American, independently studied stellar properties in the early 1900s. Hertzsprung plotted temperature versus absolute magnitude for stars in clusters. Russell did the same, but plotted spectral type versus luminosity for nearby stars with known distances. Both of their works led to the combined known HR diagram, or Hertzsprung-Russell diagram, showing the relationship between the luminosity of the star and its temperature based on the cluster type. If you have blue giants, if you have red giants, okay. Mainly if you look at the diagram, which we took from ico.global/files, J. Barton, HR diagram JPEG. If we notice, this is the main sequence star, meaning this is where the star would spend most of its life. You have from the hotter to the colder stars, those who are in the blue are the hottest ones, and then like those who are in the red are the coldest ones, okay? Around 2500 degree Kelvin, okay? And in that main sequence, you notice there's a relationship between how hot a star is and how luminous it is. So for hotter stars of the same size, the hotter the star is, the more luminous would be, okay? It will be a more luminous light, more glowing light. On the other hand, for the smallest, for the colder ones, in the red, they will be less luminous, okay? Again, due to the lower frequency, the lower temperature. So its glow would be dimmer. Now, outside of the main sequence, you have white dwarfs, which are the dead remnants of small stars, okay? They will still be hot due to the forces of gravity. However, they're less luminous, okay, because the core had started becoming, more opaque, okay, absorbing heavier metals. Now you have the red giants. They are more hot, than their peers in the main sequence. Why? Due to the fact that they become bigger, okay, their luminosity is greater because their outer shell becomes bigger, and the red supergiants, they are almost as luminous as the blue giants. Blue giants are stars that are blue, however, they are of a massive weight. So let's analyze this diagram again. The main sequence stars are those following a diagonal pattern over here, in which the ones having the lower temperature will display a dimmer luminosity, right? For lower temperature, you have dimmer or lower luminosity on the left, and vice versa, of course. For the hotter ones, they will be more luminous. Most of a star's lifetime is spent in the main sequence again. When a star dies, if it had a small to a medium mass, it turns into a white dwarf. White dwarf like over here, okay? Still a little bit hot, okay? It's still very hot compared to its size, and less luminous. Less luminous, okay, having a dense and still hot core while its outer layer has been expelled. So the fusion fuel has been exhausted, but there's still some fusion going on for heavier metals on the inside. That's why it's very hot, like melting iron, or heavier metals. As for the red giants, these represent the latter state of a star at the verge of the end of its life cycle, before becoming white dwarfs, probably. Okay, the core contracts as the fusion process that pushes it outwardly runs out of hydrogen. However, it becomes very hot because the fusion is no longer expelling the materials outside. Okay, the fusion is kept almost at a high rate inside the core, which makes it much hotter than its peers. This leads to a detachment now of the outer layers from the core. Why? Because the core has contracted, so they expand and start to cool off the outer layers of a red giant. That's why they become red, because they are detached from the core. Hydrogen continues to fuse in a shell around the helium core. Helium starts heating up and fusion into a heavier core starts taking place. So the sequence is helium fuses into carbon and oxygen. As for the red supergiants, this is the latter state for massive, supermassive stars. Similar to red giants, except their core contracts and heats up much more enormously at a higher pressure and temperature, leading to an iron core, because a fusion of heavier materials can take place due to the high pressure. The final core type would either be a neutron star or a black hole after a supernova, after the explosion, after it implodes and rebounds back. These massive stars, usually at least 8 times greater than the Sun, witness a fusion from carbon to neon to oxygen to silicon to iron. So if you notice, for the red giants, unlike the red supergiants, the red giants, they are missing the last 2 stages. So they fuse helium to carbon to neon to oxygen, and then they stop. Why? Because there's not enough pressure and the hot temperature. However, for the red supergiants, they go from carbon, neon, to oxygen, to silicon, and finally to iron, which is a much heavier core. How can we figure out to which cluster a star belongs? We first check where a star belongs on the HR diagram based on the measurements of the temperature. And we see if it does fit on the diagonal sequence path. Based on its temperature, okay, we start seeing if the size matches up with the temperature on the HR diagram, on the diagonal, on the main sequence of the HR diagram. If its age and metallicity measured from the spectrum matches the cluster's property, which is the main sequence cluster, then it most likely belongs to that cluster. Otherwise, if it's much larger and it's red, then it's mostly a red giant or a red supergiant. We measure also the star's motion, the radial velocity, and parallax to check its conformity with the cluster, if it fits with the cluster that we are taking into consideration. So in a nutshell, we see where it sits on the HR diagram, we match it with the known clusters that we are familiar with, and verify it based on its motion and chemical makeup. All right? So based on its motion, its chemical makeup, we match it up with the convenient main sequence. So, or the convenient cluster. So again, the types of clusters that we have: the white dwarfs, the main sequence, right? The blue giant cluster, supergiant, and red giants. Okay, red supergiants and red giants. Measuring using luminosity. So the flux, again, there's a relationship between the flux and the luminosity. Again, the flux is the amount of light energy received from a star per square meters, which is watts per meter square, which is equal to the luminosity, L, divided by 4 pi r squared, which is the area of the star. Okay, now we can get, the radius using that same formula, which is r naught d equal square root L divided by 4 pi f. All right, measuring the radius and area of the star. How can we get that? We get it by using the Stefan-Boltzmann law. We can get the area of a star from which we derive the radius. So Stefan-Boltzmann law stipulates that the luminosity L is equal to the area of the star, which is 4 pi r squared, by the way, the area of the external sphere, times Stefan-Boltzmann constant, which is sigma, equal to 5.67 times 10 to the power minus 8 watt per meter squared per Kelvin to the power of 4, times the temperature to the power of 4. Okay, L equal A sigma T to the power of 4. luminosity is equal to A, the area of the star, which is the area of the sphere, is equal to 4 pi r square, r being the radius of the star, times sigma, which is Stefan Boltzmann constant, times t to the power of 4. So A equal L divided by sigma T4, R is equal, in relationship to that, square root L divided by 4 pi sigma T to the power of 4. Okay, we derived R from this equation and A from this equation, and of course I is related to R. The area is related to the radius. Area is equal 4 pi radius square. Measuring the radius of stars similar to the sun. We can establish a relationship between the luminosity of a star and that of the sun, like in conjunction, in relationship. We can have establish a relationship if we are familiar with the radius of the sun, the luminosity of the sun, we can pair that to the radius, luminosity, and temperature of the star that we are observing. The relationship is radius of the star divided by the radius of the sun is equal to luminosity of the star divided by the luminosity of the sun, this is the symbol of the sun, square root of that, times T0 or TO, which is temperature of the sun over temperature of the star, square. Okay, so R, how have we derived that? By using the Stefan Boltzmann law. R divided by RO is equal to square root of luminosity divided by 4 pi sigma, which is Stefan Boltzmann constant, times T4. So we've gotten R from the Stefan Boltzmann law, as we've seen in the previous slide, divided by square root of LO divided by 4 pi sigma TO to the power of 4, which is these are for the sun, and these parameters, the R, L, they are for the star we are observing. From that, if we continue resolving it, we get eventually R divided by RO is equal to L over LO to the power of 1/2, or square root L over LO, times TO over T square. Okay, so this is how we've gotten that. You see here, TO is up and T2 is down. They are both squared. As for the square root, you have, okay, we like remove 4 pi sigma, and you know, in the numerator and in the denominator, you get L over LO, both squared, so they are both at the power of 1/2. Hubble law and redshifting. So Hubble law is the measurement of the expansion of the universe based on the red shifting, and we're gonna explain that. At first, in a nutshell, the formula for the red shifting, okay, for the expansion of the universe, is the velocity, which is the recession velocity from the redshift, is equal to h0, or Hubble's constant, multiplied by d, which is the distance of expansion of the universe in megaparsecs. So the velocity of the redshift is equal to c, which is the speed of light, times z. Z is the redshift itself, which is how much the wavelength had shifted divided by its original value in the lab. All right, we're gonna break it more down in the next slide. So d measured in parsecs, again, 1 parsec is around 3.26 light years. Let's digress a little. What is a redshift and its byproduct, the recession velocity? Imagine you're standing at a side road here, okay, and the car moving your direction with loud music playing. So listening with keen ears, you start noticing that the rhythm of the music accelerates, right? As it moves towards your direction, in your direction, the rhythm of the music accelerates, so the frequency increases, the wavelengths become more condensed upon each other and smaller as waves compress in the time-space domain. So this is as the car gets closer, this is happening in front of your ear, as you know, from the observer's perspective. But once it passes by, right? Once the car passes by and starts moving away from your location, from the point where you're standing, the music rhythm starts stalling and dilating as a broken tape. In such case, the frequency decreases and the waves are stretching out. The waves start stretching and elongating, which you know, become wavelengths start shifting upwards. This is what is called Doppler's effect, from which we derive the redshift. So as things move closer to us, not only the sound waves, but also the light starts getting more compressed, like the wavelength shifts and become shorter as things move in our direction. But as they move away, the wavelengths become longer. This is why it's called redshifting, because the waves of the galaxies that are moving away from us, from Earth, okay, due to the expansion of the universe, let's say they had shorter wavelengths, these wavelengths get longer and longer, and they've gotten to at that point to the red range, okay, because red wavelengths are longer wavelengths. All right, so they shifted from whatever color they were to the red wavelengths. This is the great indicator of the expansion or the stretching of the universe we're living in. Same thing for a luminous object. As it travels away from a vantage point, its wavelength begins to stretch and increase opposite to its frequency decreasing, as we mentioned. A changing frequency of light means a change of color, as we notice. So, in the case of an expanding universe, the color of the galaxies moving away from us will shift from blue, green, because the frequency is getting lower, so the color will shift as well, to red, which is a longer wavelength as they move further. Actually, we've noticed the red shifting, okay, through observation, which is again due to the wavelength dilation that we call a Doppler shift. Now, how do we measure the receding velocity, okay, which is the altered speed of light due to that shifting, due to that movement. This altered speed of light is obtained from the following Doppler shifts formula. Now, this formula works for smaller redshifts, not the relativistic big shifts. For smaller redshifts, v, the velocity of a wavelength, is equal to c, which is the speed of light, times z, which is the redshift. Z is equal delta lambda over lambda. What is delta lambda? Is the lambda observed, right? The lambda, which is the original one, minus the lambda that has been stretched out. Actually, in the redshift, it is the opposite. Yeah, the new lambda that we are measuring minus the lambda that is the length of the wavelengths in the lab. So the red wavelength has a fixed length at rest without movement. Okay, we compare that with the length of the wavelengths as we're observing, which is the wavelength that is traveling away. The difference between the two, okay, is divided by the original length of wavelengths, which is lambda at rest of the red wavelengths, times c, and we get the receding velocity. We have h0, which is the constant of Hubble, and thus we can get the distance of expansion is equal to v over h0 equals cz divided by h0, Hubble's constant, which is 70. H0 has been measured by Edmund Hubble, I think, the one who sent the famous, astronomical observatory in space. So Hubble constant is 70 kilometer per second per megaparsec. So D equals Cz divided by H0. For larger redshifts, we need to use the relativistic Doppler formula based on Einstein's theory of relativity for receding light moving away. So in such case, the frequency observed equal the frequency emitted at rest, square root 1 plus velocity divided by c, divided over 1 minus velocity over c. Okay. Lambda observed, which is the lambda being measured from the distant galaxy in a specific direction, is equal to lambda at rest times square root 1 plus velocity of the receding velocity divided by c, divided by 1 minus receding velocity over c. Okay? Now, if we move these things together, so lambda observed minus lambda rest equal lambda rest times square root, because we created minus lambda rest to the left and to the right, okay, in attempt to solve the equation, okay, for z. So lambda observed minus lambda rest is equal lambda rest square root all of that minus lambda rest. Okay, we introduced minus lambda rest to the left and to the right. We did not change the equation. Okay, now we divided all the equation with lambda rest. So we've gotten lambda observed minus lambda rest divided by lambda rest is equal lambda rest square root minus lambda rest divided by lambda rest. Z, so Z, which is lambda observed minus lambda rest is equal to what? Square root 1 plus V over C divided by 1 minus V over C minus 1. We continue. So we've gotten to this point. After that, okay, minus 1, we move it to the left. You get Z plus 1 is equal square root 1 plus V over C divided by 1 minus V over C. We elevate everything to the power of 2. So you get Z plus 1 square is equal 1 plus V over C divided by 1 minus V over C. We're attempting to establish the relationship between V and Z plus 1. This is what we are doing. So Z plus 1 square minus V over C times Z plus 1 square is equal to 1 plus V over C. Okay? We are solving this equation by multiplying the denominator here with Z plus 1 square. This is what we're doing. All right, so we move everything. Okay, you have Z plus 1 square minus 1 is equal to V over C times Z plus 1 square. Okay, the one side, the unknown to the other side, and Z plus 1 square minus 1, V over C, Z plus 1 square plus 1. Okay, V over C is equal Z plus 1 square minus 1 over Z plus 1 square plus 1. V is equal to C times Z plus 1 square minus 1 divided by Z plus 1 square plus 1. Okay, you can memorize that without, sweating, getting through all the phases that we went through up to that point to get to that relationship. You can memorize that relationship between the velocity, the receding velocity, and the redshift for larger redshifts. So V equal h0d, as we know. The distance of expansion is equal to the receding velocity divided by h0, which is all of that, c times z plus 1 square minus 1 divided by z plus 1 square plus 1 over h0, which is Hubble's constant again. Okay, and the distance would be in megaparsecs or million parsecs, 1 parsec being 3.26 light years again. All right, let's talk about exoplanets. So what is an exoplanet? Actually, an exoplanet is a planet orbiting another star or sun which is outside of our solar system. Now, the thing is, though the planet size would be so relatively low to detect, there is a clever method to identify the existence of an exoplanet by measuring the dimming of the flux of the star coming to our device. Okay? Because as the planet orbits the star, what happens is that the planet is blocking a part of the flux that is coming our way, in our direction, of course. So this will result in the dimming of the brightness of the star. As we measure the peak of that dimming, okay, the peak of the lowest peak of that dip in brightness, we can infer that, and we can realize how relatively small is the exoplanet in comparison to the star itself. You see, there's no way we can see the planet on its own. Why? Because the star itself is so dim and less bright. So how are we going to see something that has only its light from the reflection against the starlight? Okay, the only way we can detect that is through the method of observing the brightness of the star around which the planet is orbiting. As we see the brightness of the star dipping to a certain level, okay, we can realize how large. First of all, we can identify the existence of the exoplanet. Second, we can measure by the difference of the brightness how small is the planet, or how big is the planet in relationship to the size of the star itself. Okay, let's get into that. So again, we are measuring the dimming of the flux of the star, which because of the planet that is blocking the light flux, a part of the light flux from its receptor, we can measure that difference and come up with the size of the planet and the radius of the planet. So let's look at that. By the way, that picture is from the European Space Agency. So how do we determine the area of the planet in relationship to the area of the star it's orbiting? The ratio of the flux that has been blocked by the planet to the flux that is, to the full flux of the star are in relationship, direct relationship between the area of the planet, which is, the area of the planet will be indicated by how much dipping that happened in the luminosity of the star versus the full flux of the star that, will represent the entire area of the star without any blockage. So the difference in brightness, meaning that the original brightness value minus the new brightness value during the lowest peak, these two values differentiated against subtracted from each other, the original brightness minus the lowest dip, divided by the full brightness or full flux, if you will, is equal to the area of the planet divided by the area of the star. So this will represent the area of the planet divided by the full area of the star. This will give us the area of the planet in relationship to that of the star. From that area ratio, we can get the radius of the planet relative to that of the star. Why? Because the area of the planet is pi r square p, and the area of the star is pi rs square, So delta F over F is equal to area of the planet divided by the area of the star, area of the planet being pi r p square, divided by pi rs square. So we get rid of the pi. It is equal to r pi square divided by rs square. So delta F over F, the difference of the flux divided by the full flux, is equal to the radius of the planet divided by the radius of the star square. This is the relationship between both. By measuring the time span between two passages of the planet, we can also get what? The period of rotation of that planet around that sun, that solar, around the star of that solar system. So we can get the first, we can start measuring the period from the beginning of the first dip, you see here, and we start calculating or counting the time up to the second dip, next dip. That time span from the first dip to the next dip, from the beginning of the first to the beginning of the next, would give us what? The period of rotation of that planet around the star. Why? Because it would have completed an entire cycle before getting back to be blocked again at the same, location. Now, once we have the radius, or once we have actually the period, we can actually get from it multiple things, like the velocity. Many things are related to the period. So at first, can we get the mass? Because using the period, you can get the velocity. All right. So let's do some review. Your gravitational force is equal to the centrifugal force if we have a circular orbit. So gmm over r square equal mv square over r. So v0, which is the velocity is equal square root gm over r. Okay. Now there's a relationship between the period, right, and the velocity. So 2 pi r, which is the full cycle, the full orbital perimeter, is equal to the velocity of orbital velocity times the period that it would take to circle an entire cycle around the star, right? It's like the distance in, based on mechanics, distance is equal velocity times the period times the time multiplied by the time it takes for us to travel that distance. So now 2 pi r, we can get the radius of the planet, okay, in relationship to the radius of the star. We already have the area and the radius of the star. So now we have the radius of the planet. We have measured the period, all right? So we can get from it the velocity as well. So P equal 2 pi r divided by V0, P equal 2 pi r square root. Now V0 is what? Is square root gm over r, correct? So P square is equal 4 pi square r square, because we've elevated everything to the square value. Pi square is equal to 4 pi square r square divided by gm over r. So pi square is equal to 4 pi square r to the power of 3 divided by gm. This is also known as Kepler's law, if you notice. It's very familiar here. So from the period, the radius value, we actually have the radius value. We have the constant of gravitation. We have everything here, and we've already measured the period. We can calculate what the mass of the star. We can calculate the mass of the star. That's big M. Now, given also that the gravitational force is equal to the centrifugal force, so once we get the mass of, we've gotten the mass of the star, we've gotten the gravitational force, we can get the mass of the planet as well, okay? We can actually get the mass of the planet, okay? We've gotten the gravitational force, we are able to calculate that as well. So based on that formula, GMM divided by r squared, we get the small m of the planet in relationship to the star, okay? There are multiple ways we can get that actually, okay? In case I've lost you at some point. So using the Doppler method by measuring the blue shifting of light as the planet is rotating inwardly facing the direction of the observing device. So you see now the planet is rotating against itself, okay? When it comes our way, it's rotating in our direction. What happens is that the blue light coming, it will incur a Doppler shift, okay? Which is a blue shifting when the light is coming in our direction as the planet rotates inwardly, and it's a redshift as, you know, there's a blue shift in the direction where it's rotating to our side, and a redshift, the part of the planet that it's rotating away, okay? By measuring that, we can get the speed of rotation of the planet around itself, around its own axis, all right? So you have the period is equal to pi rp. We can get the period of the planet around its own axis. So the period is equal to pi, the radius of the planet, divided by the recession velocity that we can get from the blue shift here. Because as it's rotating inwardly, wavelength is shifting, like it's increasing in frequency. We can get that shift, and from which deduce the velocity v0, correct? Not the receding velocity for the redshift, but it would be like an increasing velocity due to the blue shift. Thank you so much for watching, and I hope you enjoyed this course, and we may see you in another courses. Bye bye.